You are listening to Seamless Systems, enterprise integration patterns for modern developers. Like and subscribe to keep up to date on our latest audiobooks. Seamless Systems, enterprise integration patterns for modern developers. Chapter 1, The Integration Imperative, Why Patterns Matter. The year is 2024, and the digital economy thrives on connections. From booking a flight online to streaming your favorite movie, from managing supply chains to running complex financial transactions, everything relies on bits and bytes flowing between different software systems. We live in a world of distributed systems, where multiple, independent software components work together to achieve a larger goal. But as anyone who has tried to coordinate a surprise party knows, getting independent entities to work together seamlessly is rarely straightforward. Consider a simple, everyday scenario: ordering a coffee through a mobile app. When you tap Order Now, multiple things happen behind the scenes. The app sends your order details to an order management system. The order management system needs to check if the items are in stock through an inventory system. It then communicates with a payment gateway to process your payment. Once confirmed, it might notify the coffee machine automation system to start brewing. Finally, it updates your loyalty points in a customer reward system, and perhaps sends you a confirmation email via a notification service. Each of these systems might be developed by different teams, using different programming languages: Java, Python, Node.js, different databases, and running on different servers or cloud platforms. The challenge is immense. How do you get them all to speak the same language, understand each other's needs, and react reliably when one part of the chain falters? The pain of ad hoc integration. In the early days of software, when systems were monolithic, a single, large application containing all functionality, integration was often simpler, if limited. Data might be passed directly within the same application or through periodic batch file transfers. But as businesses grew and technologies advanced, the need for real-time, dynamic connections became critical. Without a structured approach, developers often resort to ad hoc integration. This usually means writing custom code for every single connection. This system needs data from that one, so I'll write a script to pull it directly from its database. System A needs to tell System B something, so I'll create a direct API call from it to B. System C needs to know when System D changes, so I'll set up a cron job to pull D every few minutes. While these point-to-point connections might seem easy at first, they quickly lead to what's colloquially known as integration spaghetti. Imagine a diagram of all your systems, with lines representing every custom connection. Soon, it looks like a plate of tangled noodles. This spaghetti is brittle, complex, and prone to breaking. Fragility: if System B changes its API, System A's custom code breaks. You need to identify every connection to System B and update it. Scalability issues: direct connections often tie up resources, making it hard for systems to scale independently. Lack of insight: it's difficult to understand the overall flow of data or diagnose problems when everything is custom code. High maintenance cost: every modification or new integration adds to the spaghetti, making it exponentially harder and riskier to change. This integration spaghetti becomes a significant bottleneck, stifling innovation and draining development resources. Businesses become too rigid to adapt to new market demands. The evolution of system architectures. From monoliths to microservices, the quest for agility and scalability led to architectural shifts that, ironically, amplified the integration challenge. Service-oriented architectures, SOAs, early attempts to break down monoliths into smaller, loosely coupled services. This introduced the concept of enterprise service buses, ESBS, as central intermediaries for routing and transforming messages. While ESBS promised a lot, they often became their own monolithic bottlenecks, sometimes referred to as smart pipes, dumb endpoints. We'll explore this later. Microservices architectures, the current dominant paradigm, pushing for even smaller, highly independent services, each responsible for a single business capability. While microservices offer unprecedented flexibility and scalability, they inherently bring more services that need to communicate reliably and efficiently. The integration problem moves from a single, large application to a network of many small ones. Event-driven architectures, EDAs, a powerful pattern where services communicate by publishing and consuming events, facts about something that happened. This moves integration from direct calls to passive observation, fostering even looser coupling. However, managing event streams and ensuring reliable processing introduces new complexities. Cloud-native and serverless. Deploying applications on cloud platforms like Oz, Azure, or Google Cloud, often using serverless functions, means leveraging managed services for messaging, databases, and APIs. These platforms abstract away infrastructure, but still require careful design of how components integrate. In essence, while our ways of building individual systems have become highly sophisticated, the fundamental need for them to interact remains. And with increasing distribution, the complexity of these interactions has skyrocketed. The power of patterns, a shared language for solutions. This is where enterprise integration patterns come into play. Just like design patterns, like the iterator or factory patterns, provide proven solutions for object-oriented programming challenges, EIPs offer a catalog of well-defined, robust solutions for common integration problems. They are not specific technologies or products. They are conceptual templates that describe how to solve a particular problem in a particular context. Think of it like this. If you're building a house, you don't invent a new way to build a wall every time. You use established patterns: brick walls, stud walls, concrete walls. You use standard components like doors and windows. You have a shared understanding of what a foundation or a roof truss is. This common understanding streamlines the building process, ensures quality, and allows different tradespeople to collaborate effectively. Similarly, enterprise integration patterns provide a common vocabulary. When a developer says content-based router, everyone on the team knows exactly what they mean. A component that directs messages based on their content. No need for lengthy explanations or custom diagrams. Proven solutions. These patterns have been battle-tested in countless real-world scenarios. They represent collective wisdom on how to approach recurring problems. Reduced complexity. Instead of reinventing the wheel with custom, tangled code for every integration, you apply a well-understood pattern. This simplifies design, development, and maintenance. Better communication. Patterns facilitate discussions among architects, developers, and even business stakeholders, allowing everyone to conceptualize the integration strategy. Scalability and robustness. Many patterns inherently promote loose coupling, asynchronous communication, and fault tolerance, qualities essential for scalable and resilient distributed systems. A glimpse ahead. Over the coming chapters, we will embark on a journey to demystify these powerful patterns. We'll start with the fundamental building blocks of integration: the message itself, the channels through which messages flow, and the endpoints where systems interact. Then, we'll systematically explore patterns in categories like message routing, transformation, error handling, and system management. Crucially, we'll always tie these classic patterns back to their application in modern microservices and event-driven architectures. Our aim is to move beyond the integration spaghetti and transition towards seamless systems, beautifully orchestrated, efficient, and resilient connections that power the digital enterprise. The journey begins with understanding the core components. Chapter 2: Foundations of Integration, Messages, Channels, and Endpoints. In the previous chapter, we established why integration is crucial and why relying on ad hoc, point-to-point connections quickly leads to an unmanageable mess. We also introduced the idea of enterprise integration patterns as a way to bring order to this complexity. But before we dive into specific patterns like routers or transformers, we need to understand the fundamental building blocks upon which almost all integration solutions are built. Just as a language is built from words, phrases, and grammar rules, integration systems are built from three core concepts: messages, message channels, and message endpoints. These three elements form the essential toolkit for any developer tackling integration challenges. Think of sending a letter. What are the key components involved? You have the actual letter itself, the content or information you want to convey. You put it in an envelope, address it, and perhaps add a stamp. This is the message. Then you drop it into a mailbox and the postal service takes over. The network of mail trucks, sorting facilities, and delivery routes represents the message channel. Finally, the letter arrives at the recipient's mailbox, where they retrieve it and read it. That mailbox, acting as the sending and receiving point for the letter, is the message endpoint. This simple analogy holds true for how software systems integrate, understanding the message. At the heart of any integration is the message. A message is essentially a parcel of information that one system sends to another. It's the unit of data exchange in a distributed environment. Unlike a direct function call in a monolithic application, where parameters are passed and a return value is expected immediately, a message is typically asynchronous and self-contained. What goes into a message? Every message should have two main parts. Header, this is like the envelope of our letter. It contains metadata about the message itself, not the business information. Common header fields include correlation ID, a unique identifier that links related messages together, e.g., a request message and its corresponding reply message. This is incredibly useful for tracing a transaction across multiple systems. Timestamp, when the message was created or sent. Message type, what kind of information does this message convey, e.g., order placed, payment failed, inventory update. Sender recipient information, who sent it or who it's intended for. Return address, where to send a reply if one is expected. Expiration date, when the message should no longer be considered valid. Priority, how important or urgent the message is. Body or payload. This is the actual content of the message, the business data. If our message is an order-placed message, the body would contain details like the customer ID, items ordered, quantities, price, shipping, address, etc. The format of the body can vary widely. Text, simple strings. XML, extensible markup language, a structured tag-based format, historically very popular. JSON, JavaScript object notation, a lightweight, human-readable format, now the de facto standard for web services and APIs. Binary, raw byte streams for images, video, or highly optimized data. Why is a message more than just data? A message isn't just a chunk of data. It's a complete, self-describing unit that allows independent systems to interact without needing to know too much about each other's internal workings. By packaging data with relevant metadata in the header, the message becomes robust and portable. This separation of concerns, what the message is about, body, versus how it should be handled, header, is foundational to flexible integration. Message channels, the pathways of communication. Once you have a message, you need a way to send it from one system to another. This is the role of a message channel. A message channel is a logical pathway through which messages flow. It abstracts away the underlying communication mechanism, whether it's a network socket, a database table, a queue, or a cloud service topic. Developers send messages to a channel and receive messages from a channel, without necessarily knowing the intricate details of what happens in between. The original EIP book primarily focused on messaging systems, like message queues or brokers, as the implementation of channels. In modern architectures, channels can be conceptualized broadly, encompassing message queues, like a single line at a bank where messages wait their turn. Message topics, like a public bulletin board where anyone can post and anyone interested can read. HTTP endpoints, a web service URL that accepts requests. Database tables, used for polling or shared state. Files, for batch processing. Regardless of the underlying technology, the concept of a channel remains the same. It's the conduit for messages. There are two primary types of message channels that form the basis of most integration patterns. Point-to-point channel. Analogy, a direct conversation between two specific people, or a traditional postal letter addressed to one unique recipient. Functionality, a message sent to a point-to-point channel will be delivered to exactly one receiver. Even if multiple receivers are listening to the channel, only one of them will get the message. Once delivered, the message is effectively consumed by that receiver and removed from the channel. Use cases, task distribution, work queues, ensuring a message is processed only once, e.g., processing a payment. Think of a taxi queue. A taxi takes one passenger, and that passenger is gone from the queue. How it's implemented. typically using message queues, e.g., RabbitMQ queues, Kafka consumer groups with one partition per consumer, AWS SQS queues. Publish-subscribe channel. Analogy: a newspaper subscription. Multiple subscribers receive their own copy of the same newspaper, or a public announcement system. Functionality: a message sent to a publish-subscribe channel will be delivered to all interested subscribers. Each subscriber receives its own copy of the message, and the message typically remains available on the channel for subsequent subscribers for a defined period or until consumed from their specific subscription. Use cases: broadcasting events, e.g., order placed event, product price updated event, notifications, data replication, decoupling publishers from multiple consumers. How it's implemented: using message topics, e.g., Kafka topics, AWS SNS, GCP PubSub, RabbitMQ exchanges with fanout. Why is the distinction between these two channel types so important? Choosing the right channel type is fundamental to your integration design. If you need a task processed exactly once, a point-to-point channel, queue, is your friend. If you have an event that multiple independent systems need to react to, a publish-subscribe channel topic is the way to go. Misusing them can lead to data loss, duplicate processing, or tightly coupled systems. Message endpoints: the system's voice and ear. Finally, we have message endpoints. While the message is what is sent, and the channel is how it's sent, the message endpoint is where it's sent from and where it's received. It's the point where a particular application or system connects to a message channel. Think of it as an adapter between your internal system logic and the external messaging world. Rather than your application code directly interfacing with complex queue APIs or network protocols, it interacts with a simpler message endpoint. There are two main types of message endpoints: message sender or producer publisher. Functionality: this endpoint is responsible for translating an application's internal data structures or events into a message format and sending it to a message channel. Example: in our coffee ordering app, when the order management system wants to notify the payment system, it packages the order details into an order payment message and sends it via a message sender to the appropriate channel. The application code simply says "send this data," and the sender figures out the message format and channel details. Message receiver or consumer subscriber. Functionality: this endpoint listens to a message channel, receives incoming messages, and translates them from the message format into a form that the application's internal logic can understand and process. Example: the payment gateway system has a message receiver listening to the payment request channel. When an order payment message arrives, the receiver extracts the payment details and passes them to the payment processing logic within the system. The role of the message gateway, closely related to the message endpoint, is the message gateway. This pattern provides a clean separation between your business logic and the underlying messaging infrastructure. Instead of your core application code knowing about specific channels or message structures, it interacts with a simple, technology-agnostic interface provided by the message gateway. The gateway then handles all the complex message construction, routing, and channel interactions internally. This makes your business logic cleaner, easier to test, and more resilient to changes in your messaging infrastructure. Analogy: imagine a universal adapter plug. Your device application connects to the adapter with its standard plug, business logic sending, receiving, and the adapter message gateway handles all the different wall sockets, messaging systems. Putting it all together, the pipes and filters concept, while not a pattern for individual components, the pipes and filters architectural style elegantly describes how these foundational elements come together. Imagine an assembly line in a factory. The raw materials messages flow along a conveyor belt channel. At various stations along the belt, specialized machines, filters endpoints, perform specific, independent tasks on the materials, e.g., cutting, shaping, painting. Each machine takes input from one part of the belt and places its output onto another part of the belt for the next machine. In software integration, a pipe is essentially a message channel, and a filter is a component that processes a message, potentially transforms it, and then sends it on. Each filter has a well-defined input and output, operating independently. Example: An order processing flow might look like order placed message, validation channel pipe, order validator filter, enrichment channel pipe, discounts enricher filter, payment channel pipe, etc. This elegant model promotes modularity, each filter does one job well; reusability, filters can be recombined in different pipes; testability, each filter can be tested in isolation; scalability, independent filters can be scaled independently. Conclusion: the core vocabulary for seamless interaction. Messages, message channels, and message endpoints are the ABCs of enterprise integration. They provide the fundamental vocabulary and conceptual framework for understanding how distributed systems can communicate effectively, reliably, and with minimal coupling. By grasping these core concepts, you're now equipped to understand the more sophisticated patterns we'll explore in the following chapters. Patterns that leverage these building blocks to tackle complex routing, transformation, and error handling challenges. The journey to seamless systems begins with knowing your basic tools. Chapter 3, the Messaging Toolkit Channels, Pipes, and Filters. In Chapter 2, we established the fundamental building blocks of integration: the message, what is sent; the message channel, how it's sent; and the message endpoint, where it's sent from and to. These are like the individual words in our language of integration. But just like words are combined to form sentences, paragraphs, and stories, these fundamental components are combined to create powerful and flexible integration flows. This chapter delves into the first set of enterprise integration patterns that help us assemble these building blocks into meaningful sequences, creating sophisticated messaging toolkits for our systems. We'll explore how to direct, manipulate, and combine messages using patterns that embody the pipes and filters architectural style. Deconstructing pipes and filters, building the assembly line. Recall the pipes and filters analogy from Chapter 2. An assembly line where raw materials messages move along conveyor belts channels and are processed by specialized machines, filters. This powerful architectural style is not just an analogy, it's a fundamental principle for designing robust and modular integration solutions. Filters. In this context, a filter is any component or service that performs a specific, well-defined task on a message. It receives a message, processes it in some way, and then typically, though not always, produces an output message. Each filter is independent, focused on a single responsibility. Examples of filter tasks include validating data, transforming formats, enriching information, or even making routing decisions. Pipes. These are the message channels we discussed. They connect filters, acting as the conduits through which messages flow from one processing stage to the next. The beauty of pipes is their ability to decouple the filters. A filter doesn't need to know who produced the message it received or who will consume the message it produces. It only interacts with the channel. The pipes and filters style promotes modularity. Each filter stands alone, making it easy to understand, develop, and maintain. Reusability. A filter developed for one message flow can often be reused in different contexts simply by connecting it to different pipes. Testability. Because filters are independent, they can be tested in isolation, simplifying quality assurance. Scalability. Different stages of the pipeline can be scaled independently based on their processing demands. If one filter becomes a bottleneck, you can simply add more instances of that filter to concurrently process messages from its input channel. Now, let's look at specific patterns that act as our filters or help orchestrate messages within these pipelines. Basic message manipulation, the message filter. While not explicitly a routing pattern, the message filter is a logical first step in message manipulation within a pipeline. The problem: not every message produced by one system or stage is relevant to every subsequent system or stage. Sending irrelevant messages downstream can waste processing resources, clog channels, and complicate the logic of receiving systems. The solution: a message filter intercepts messages and passes them on only if they meet certain predefined criteria. If a message does not satisfy the criteria, it is discarded or sent to an alternative channel, perhaps a dead letter channel, as we'll see in a later chapter on error handling. Analogy: imagine a security checkpoint at an airport. It allows only passengers with valid boarding passes and non-prohibited items to proceed. Everyone else is rejected or diverted. How it works. The filter typically inspects the message header or body for specific values, absence of values, patterns, or conditions. Benefits: reduces load on downstream systems, simplifies logic in consuming applications that no longer need to check for irrelevant messages, and improves overall system efficiency. For example, an order processing system might use a message filter to ensure that only paid orders proceed to the fulfillment stage, filtering out any orders that are still pending payment. Directing the flow. The message router. Once messages are filtered for relevance, the next logical step is often to direct them to the correct processing path. This is the domain of the message router. The problem. In a complex integration scenario, messages often flow through a central point, but need to be dispatched to different downstream systems or processing paths based on various conditions. A single input channel might need to feed multiple potential output channels. The solution. The message router is a component that consumes messages from a single input channel and, based on some logic, publishes each message to one of several output channels. It doesn't modify the message content itself. Its sole responsibility is to decide where the message should go next. Analogy: think of a railway switch in a train yard. All trains arrive on one track, but the switch directs them to different tracks based on their destination. The trains themselves aren't changed, just their path. Key concept. The routing logic can be as simple or as complex as needed, often relying on rules configured within the router. Intelligent routing, the content-based router. A specialized and very common form of the message router is the content-based router. The problem: often, the decision of where to send a message depends not just on simple message properties, but on the actual business data contained within the message's body, its content. The solution. A content-based router inspects the contents of a message and uses that information to determine the message's next destination channel. This pattern allows for highly dynamic and context-aware routing. Analogy. Our postal sorting machine returns here. It doesn't just look at the envelope's color, a header property. It reads the recipient's address, content, to determine which delivery route the letter should go on. Or imagine a call center system that routes your call to the technical support department if you mention login issue, but to billing if you say invoice. How it works. The router extracts specific data points from the message's payload and applies a set of rules or expressions to them. For instance, an order message might be routed to different inventory systems based on the product category field within its body, e.g., books to one system, electronics to another. Benefits. Enables granular, flexible routing decisions, supports heterogeneous systems with specific processing needs, and allows for changes in business logic to affect routing without modifying downstream systems. The content-based router is indispensable when you have diverse processing units that specialize in different types of data or transactions. Broadcasting and splitting. Recipient list and splitter. Sometimes, a message needs to go to multiple places, or it contains multiple things that need individual attention. The recipient list. Brief introduction. The problem: a single message needs to be processed by multiple independent systems or components. Or, a message needs to be dynamically sent to a set of recipients that can change at runtime. The solution. The recipient list pattern is a variation where a message router sends a copy of the message to each channel in a dynamically determined list of recipients. It's essentially a broadcasting mechanism for specific, identified consumers. Analogy: sending an email to a group of people where everyone on the list gets their own copy. How it works. The router determines a set of target channels, the recipient list, based on the message content or other criteria, and then publishes the message to each channel on that list. Note: we'll explore the recipient list more deeply in Chapter 4, as it often works in conjunction with other complex routing patterns. The splitter. The problem: a single, large message contains multiple distinct logical pieces of information that each need to be processed independently. For example, a purchase order might contain details for several different items, and each item needs to undergo separate inventory checks. Processing the entire message monolithically might be inefficient or complex. The solution: a splitter takes one incoming message and breaks it down into several smaller, independent messages. Each of these smaller messages can then be processed individually and often in parallel by different filters in the pipeline. Analogy: think of a large package arriving at a warehouse that contains several different types of goods, e.g., books, electronics, toys. The splitter is the person who opens the large package, separates the items, and puts each individual item on its own conveyor belt heading to the appropriate department. Or a food processor chopping a whole apple into many small slices. How it works: the splitter identifies repeating elements or logical subdivisions within the original message's content and creates a new message for each identified piece. Each new message will typically inherit necessary header information, like a correlation ID, from the original message to ensure that these fragmented pieces can be linked back together later if needed. Benefits: enables parallel processing, simplifies downstream logic, each component deals with a smaller unit of work, and allows for more granular error handling. Combining back: the aggregator, brief introduction. Complementary to the splitter, there's often a need to bring those split-up messages back together. The problem: after a message has been split and its individual parts have been processed, possibly by different systems, in parallel, or out of order, you often need to combine the results back into a single, cohesive message representing the original logical unit. The solution: an aggregator collects a set of related messages and combines them into a single, outgoing message. It waits until all expected parts of a group of messages have arrived before releasing the aggregated message. Analogy: the aggregator is like the person in the warehouse who collects all the processed individual items that belonged to the original large package and reassembles them into a new, consolidated shipment, or collecting all the pieces of a puzzle to form the full picture. Key concept: aggregators rely heavily on the correlation ID from Chapter 2 carried in the message headers. This ID tells the aggregator which incoming messages belong to the same logical group. The aggregator also needs a completion strategy, rules that tell it when all parts of a group have arrived, e.g., count of messages, a timeout, or a special last message signal. Note: the splitter and aggregator often work together as a pair. We will delve much deeper into the complexities of aggregators, including their completion strategies and handling of potential missing messages in Chapter 4. Conclusion: mastering the flow. In this chapter, we've explored the initial patterns that empower developers to build intelligent and dynamic messaging pipelines. From filtering out irrelevant messages to expertly routing them based on their content, and even breaking down a single large message into many smaller, manageable units, and anticipating their reassembly, these patterns represent powerful tools in your messaging toolkit. They enable you to orchestrate complex message flows, promoting modularity, scalability, and resilience in your distributed systems. These patterns: message filter, message router, content-based router, recipient list, splitter, and aggregator, form the foundational logic for directing and reshaping your message flows. In the next chapter, we'll dive deeper into the world of routing, exploring more advanced techniques for ensuring your messages always find their way to the right destination. Chapter 4: Routing decisions, routers, splitters, and aggregators. In the previous chapter, we introduced the message router as a component that directs messages to the correct channels. We also briefly touched upon the splitter and the aggregator as a pair for breaking down and reassembling messages. This chapter will dive deeper into these crucial patterns, exploring their nuances, complexities, and how they combine to orchestrate sophisticated message flows and make intelligent routing decisions within your integrated systems. These patterns are the traffic cops, mail sorters, and assembly line supervisors of your data, ensuring everything goes where it needs to and comes back together as required. Intelligent dispatch. Deeper into the content-based router. The content-based router is arguably one of the most frequently used routing patterns. Its power lies in its ability to examine the actual data within a message, not just its sender or channel, to make a routing decision. How it works revisited. A content-based router consumes messages from one input channel. It then applies a predefined set of rules or conditions based on the message's content, e.g., values in the payload, specific attributes in the message body, to determine which output channel the message should be sent to. Each rule typically maps to a specific destination. Defining the rules, the routing rules can be implemented in various ways. Simple predicates. Basic if-else statements checking for exact matches or range values, e.g., if order amount 1000 send to large order channel. Expression languages. Using more expressive languages like XPath for XML messages, JSON path for JSON messages, or even custom domain-specific languages, DSLS, to extract values and define conditions. External rule engines. For very complex or frequently changing business rules, a dedicated rule engine might be integrated. This allows business analysts to manage routing logic without developer intervention. Common scenarios for content-based routers. Order processing. Routing orders to different warehouses based on shipping address or to different fulfillment centers based on product category. Customer service. Directing customer inquiries to different support queues based on the query type or customer's VIP status. Data synchronization. Sending updates to different downstream systems based on the type of data change, e.g., user profile updates to CRM, product updates to e-commerce, price changes to analytics. API versioning, A/B testing. Routing API requests to different backend service versions or experimental features based on header values or user IDs. Considerations. Rule order. If multiple rules could apply, the order in which they are evaluated matters. Default route. It's good practice to have a default or fall-through route for messages that don't match any specific criteria, often leading to an error channel or a log. Performance. For extremely high message volumes, complex content parsing and rule evaluation can impact performance. Maintainability. As routing rules become more complex, managing and testing them can become challenging. Dynamic distribution, the recipient list. While the content-based router sends a message to one out of many possible destinations, the recipient list pattern is used when a message needs to be sent to multiple specific destinations dynamically. The problem? A single event or piece of information needs to trigger multiple, potentially independent actions in different parts of a system, and the set of recipients may not be fixed, but depends on the message itself or external factors. The solution? The recipient list takes an incoming message, determines a list of target channels for that particular message, and then sends a copy of the message to each channel in that list. Critically, these are separate copies, so each recipient can process its copy independently. Analogy: imagine a project manager who, after a project milestone is reached, sends out different notifications. One to the billing department, another to the marketing team, and a third to the development lead, each with slightly tailored information. The manager has a dynamic list of who needs to know what. How the list is determined. From message content, the message itself might contain a list of relevant recipients or attributes that can be used to look up recipients, e.g., an event message that lists all stakeholders who need to be notified. External service lookup. The recipient list logic might call an external directory or configuration service to determine the current list of interested parties for a given message type. Use cases. Event broadcasting for specific consumers. When an order-placed event occurs, you might want to send it to the billing system, the inventory system, and the customer notification service. Each system needs its own copy. Workflow coordination. After a step in a workflow is completed, a message might trigger the next parallel steps by sending a copy to each subprocess. Audit and logging. Sending a copy of sensitive messages to an auditing system in addition to their primary destination. Contrast with publish-subscribe channel. A publish-subscribe channel, from Chapter 2, sends messages to all subscribers who have explicitly registered interest with the channel. The publisher doesn't explicitly know or care who the subscribers are. It's a broad broadcast. A recipient list determines the specific set of channels per message at runtime. The publisher, or the recipient list component acting on its behalf, is aware of which channels are receiving the message, even if it determines this dynamically. It offers more granular control over who receives a message based on runtime conditions. Breaking it down, advanced splitter use cases. We briefly introduced the splitter as a pattern that breaks one message into many. Let's delve into its practical applications. The problem: processing a large message that contains a collection of individual items, e.g., a batch file of orders, an XML document representing many invoices, a single API request for multiple product updates, can be inefficient. It's often better to process each item independently and in parallel. Types of splitting: iterating collections, splitting a message containing a list or array of objects where each object becomes a new message. Delimited content. For text messages, splitting based on a delimiter, e.g., a newline character for a file with one record per line. XPath/JSON path expression. For structured data, using expressions to identify repeating nodes or elements, e.g., splitting an XML order into individual item messages. Crucial for distributed processing. The splitter is fundamental for achieving parallelism and isolating failures. If processing one item fails, it doesn't necessarily block or fail the processing of other items from the same original message. Correlation IDs for split messages. When a message is split, each new individual message must carry identifying information that links it back to the original message and its siblings. This is typically done by copying the original message's correlation ID into the header of each split message. Often, a sequence number and sequence size are also added to the headers of the split messages. For example, correlation ID: order batch XYZ2, 02400315. Sequence number: 15 for the first message out of 5. Sequence size: 5. This metadata is vital for the aggregator pattern. To reassemble the results, piecing it together, the intricacies of the aggregator. The aggregator is the complementary pattern to the splitter, bringing together related messages into a single, cohesive unit. It's often more complex to implement than the splitter due to the challenges of managing asynchronous arrival and ensuring all parts are collected. The problem: after a message has been split, or multiple systems have responded to a request, the results or responses from these individual processing steps need to be combined into a single, meaningful message for subsequent processing or for returning to the original requester. Core mechanics: correlation. The aggregator relies heavily on the correlation ID and sometimes group ID to identify which incoming messages belong to the same logical group. It acts like a post office sorting mail into different boxes based on sender or common reference number. Collection. Messages belonging to the same group are collected and temporarily stored, e.g., in an in-memory buffer or a persistent store. Completion strategy. This is the most critical part of an aggregator. It defines when a group of messages is considered complete and ready for aggregation. Common strategies include count-based. Aggregates after a predefined number of messages have arrived, e.g., 5 out of 5 items processed. This works well when the sequence size is known. Sequence-based. Checks for specific sequence number headers to ensure all parts have arrived in order, if order matters, or that a specific last message has been received. Timeout-based. Aggregates whatever messages have arrived within a specified time limit, even if the expected count isn't met. This is crucial for resilience against missing messages or slow responses. If a timeout occurs, the partially aggregated result may be sent, or the incomplete group may be discarded or sent to a dead letter channel for investigation. Marker-based. A special end-of-sequence message or a specific flag within a message signals completion. Conditional. A specific condition based on the content of the arriving messages indicates completion, e.g., a completed status flag appears in one of the messages. Handling missing messages failures. What happens if one of the messages from a group never arrives? Without a timeout, the aggregator could wait indefinitely, leading to resource leaks. Timeouts are essential to prevent indefinite waiting. Strategies include releasing partial results, discarding the group and sending an error notification, or having a retry mechanism for the missing part. Resilience and idempotence. Aggregators must be designed to handle duplicate messages if the underlying channel guarantees at least once delivery, and ensure that aggregation logic is idempotent, i.e., Processing the same message multiple times doesn't change the outcome or cause an error. This typically involves tracking processed messages for a given correlation ID. The powerful combination, scattergather. One of the most frequently used compound patterns in integration is scattergather. It perfectly illustrates the combined power of a recipient list or splitter with an aggregator. The problem: you need to send a single request or piece of information to multiple services in parallel scatter, collect their individual responses, and then combine those responses into a single, consolidated result, gather. The solution: scatter. The initial message is sent to a recipient list to query multiple known services or passed through a splitter if the request needs to be broken down into subrequests for parallel processing. Each outbound message carries a correlation ID. Processing: each of these scattered messages is processed independently by different services or components. Gather: the responses from these services, which also carry the correlation ID, are collected by an aggregator. The aggregator waits until all expected responses have arrived, based on its completion strategy, and then combines them into a single response message. Analogy: a travel agent, the scattergather pattern, receives a request for a flight. They send inquiries to multiple airlines, scattering the request. Each airline responds with flight options and prices. The travel agent gathers all these responses and presents the customer with a single consolidated list of the best options. Use cases: price comparison services, querying multiple vendors for the best price for a product. Search engines, sending a query to different indexed data sources and combining the results. Workflow orchestration, kicking off parallel subworkflows and waiting for all of them to complete before moving to the next main step. Ordering the chaos, the resequencer. In asynchronous systems, especially when messages travel through different paths or are processed by concurrent components, messages might arrive out of their original sending order. However, many business processes require strict ordering. The problem: messages that logically belong in a sequence, e.g., status updates for a single order, pending, processing, shipped, may arrive out of order, leading to incorrect state updates or business logic errors. The solution: a resequencer holds incoming messages and ensures they are delivered to the downstream consumer in the correct sequence. Analogy: imagine a busy airport control tower. Planes arrive continuously, but they are only cleared to land in a specific, determined order to avoid collisions and manage runway traffic. The tower holds planes in a waiting pattern until their turn. How it works: sequence identification. Messages must carry sequence metadata in their headers, e.g., sequence number, group ID. Buffering. The resequencer maintains an internal buffer where it temporarily stores out-of-sequence messages. Release strategy. When the next expected message in a sequence arrives, it, and any subsequent messages now in sequence, is released. Timeouts. Crucially, resequencers must have a timeout mechanism. If an expected message doesn't arrive within a certain period, the resequencer must decide whether to release what it has, thus accepting a gap in the sequence, discard the buffered messages, or signal an error. Without timeouts, a missing message could cause the resequencer to endlessly wait, leading to a bottleneck. Considerations: resequencers can introduce latency, as messages are held, and require careful management of their buffers and timeout strategies. They are essential where exactly once-in-order processing is a hard requirement. Conclusion: orchestrating the flow with precision. The patterns discussed in this chapter, the content-based router, recipient list, splitter, aggregator, and resequencer, are indispensable for building sophisticated and resilient integration solutions. They move beyond simply connecting systems to intelligently directing, manipulating, and reordering messages to support complex business processes. By understanding their individual roles and how to combine them, especially in patterns like scattergather, you gain the power to design highly concurrent, fault-tolerant, and adaptable integration architectures. In the next chapter, we will shift our focus from directing message flow to transforming the messages themselves, ensuring different systems can always understand each other's data regardless of their internal formats. Chapter 5. Transforming data, translators, normalizers, and enrichers. In the interconnected world of enterprise systems, passing messages between different applications is crucial. We've discussed how to identify, filter, and route these messages with precision. But what happens when System A speaks in terms of product codes and uses XML, while System B expects item numbers and communicates in JSON? Routing a message to the correct destination is only half the battle. Ensuring the message is understood by the recipient is the other, equally critical, half. This is where data transformation patterns come into play. Systems rarely store or represent the exact same information in the exact same format. This fundamental difference, known as impedance mismatch, arises for many reasons. Historical development. Systems built at different times, by different teams, or with different technologies. Domain specificity. Each system is optimized for its own specific business domain, leading to unique data models and terminology. External integration. When integrating with third-party vendors or external services, you have no control over their data structures. Without transformation, integrating these disparate systems would be impossible or would require each system to understand every other system's nuances, leading to the dreaded integration spaghetti we discussed in Chapter 1. The patterns in this chapter provide elegant solutions to bridge these data gaps. The data gap, message translator. At the core of bridging data format differences is the message translator. The problem: System A produces data in a certain format or structure, e.g., an XML document with specific tags describing a customer order. System B, however, expects the same information, but in a different format, e.g., a JSON object with different field names and nesting, or even a different type, e.g., converting a string to an integer. The solution: a message translator is a component that converts a message from its source format structure into a target format structure. It acts as an interpreter, ensuring that the semantic meaning of the message is preserved even as its representation changes. Analogy: imagine a universal human language translator. One person speaks French, another speaks Spanish. The translator listens to the French, processes its meaning, and then articulates that same meaning in Spanish. The words change, but the core message remains the same. Types of translation: format transformation, converting between XML, JSON, CSV, fixed width text, or even binary formats. Structural transformation, changing the hierarchy of data, e.g., flattening nested structures, creating new nested objects from flat data. Field mapping renaming, changing the names of fields, e.g., cust ID to customer identifier. Value translation, converting specific values, e.g., M to male, 1 to true. Data type conversion, changing a string representing a number into an actual numeric type. Implementation considerations, rules-based mapping, defining explicit rules for how source fields map to target fields, including any necessary transformations, e.g., source price 1.05 for a target calculated field. Tools, specialized tools like XSLT for XML transformations, Jolt for JSON transformations, or various enterprise application integration. EAI platforms often provide visual or declarative mapping capabilities. Custom code, for complex or dynamic transformations, custom code, e.g., a small microservice function, might be written. Benefits: allows systems to remain decoupled, avoids forcing existing systems to adapt to new formats, and facilitates smooth data flow across diverse technology stacks. The canonical data model, a universal language. While the message translator solves the direct format mismatch between two systems, consider a scenario with many systems, System A, B, C, D, that all need to exchange data. If System A needs to talk to B, C, and D, and System B to A, C, and D, and so on, you would need a myriad of direct translators, N1 unique translators for N systems. This quickly becomes unmanageable. The problem: the spaghetti we discussed earlier doesn't just apply to direct connections, but also to managing different data formats across many applications. Maintaining a growing number of point-to-point translators for every pair of systems is a nightmare. The solution: introduce a canonical data model. This defines a single, enterprise-wide, universal data format and structure for a specific business entity, e.g., a customer model, an order model. Instead of translating directly between every pair of systems, each system only needs to know how to translate its internal format to and from this canonical model. Analogy: imagine the United Nations. Instead of every diplomat needing to speak every other diplomat's language, they all agree to conduct official business in a few common languages, e.g., English, French, Spanish. Each diplomat only needs to learn to speak and understand these common languages, not all 193 plus national languages. How it works. When System A sends a message, it translates its internal format into the canonical data model. The message, in canonical form, then travels through the integration layer. When System B receives the message, it translates the canonical data model into its own internal format. Benefits: reduced complexity. Instead of N1 translators, you only need 2 N translators, one to canonical, one from canonical for each of N systems. Improved maintainability. Changes to a system's internal data model only require updating its single translator to the canonical form, not translators to every other system. Onboarding new systems. New systems can be integrated more easily by just developing their 2 translators to and from the canonical model. Consistency promotes a common understanding of key business entities across the enterprise. Challenges: design difficulty. Designing a robust and flexible canonical model that satisfies the needs of all or most systems can be complex and requires significant upfront effort and consensus. It often represents the least common denominator, combined with the most common superset. Performance overhead. Every message passes through 2 translations, which might introduce a small performance cost. Evolution challenges. Changes to the canonical model itself can have a ripple effect across all integrated systems, requiring careful versioning and migration strategies. Despite its challenges, the canonical data model is a powerful pattern for managing complexity in large-scale enterprise integrations. Enriching the payload, message enricher. Sometimes, the message itself doesn't contain all the necessary information for downstream processing. It might only have an ID, for instance, and other details need to be looked up. The problem: an incoming message provides partial information, e.g., an order ID and a customer ID, but a subsequent processing step requires additional data related to that partial information, e.g., customer's full name, address, loyalty status, or product details like price and description. Sending the entire dataset in every message might be inefficient or create unnecessary coupling. The solution: a message enricher takes an incoming message, uses some of its data, often an ID, to query an external data source, like a database, another service, or an API, retrieves the missing information, and then adds or enriches the original message with this new data before passing it down the pipeline. Analogy: you receive a note with just a patient's medical record number. To properly treat them, you first look up their full medical history and current medications from a central database. That added information makes the patient note complete for your task. How it works: the enricher receives a message. It extracts one or more pieces of data from the message, e.g., customer ID. It performs a lookup against an external system using this data, e.g., calls the customer service API with customer ID. It receives the additional data, e.g., customer name, customer address. It injects this new data into the original message, often in a dedicated enrichment section or by appending new fields. The now enriched message is forwarded. Use cases: adding product details, name, price, category, to an order line item that only contains product ID. Appending customer demographics, age, location, to a purchase event message. Attaching shipping cost calculations based on destination and weight to a delivery message. Adding security context, user roles, permissions, to an authenticated request. Benefits: keeps messages small and focused initially, reduces redundant data in messages, centralizes data lookup logic, and promotes cleaner message contracts between systems. Considerations: introduces a dependency on the external data source, potential for network latency and associated performance impacts, and error handling if the external lookup fails or returns unexpected data, e.g., customer ID not found. Standardizing representations, normalizer. Even within the same data type, systems can use vastly different ways to represent the same concept. The problem: different systems might use different codes or formats for the same logical piece of information, e.g., gender represented as M, male, or 1. Country codes as USA, US, or United States, status as active, running, open. This inconsistency makes it difficult to compare, process, or search for data across systems. The solution: a normalizer, sometimes called a data normalizer, or value translator, transforms varying data representations into a single, consistent, and standardized format or set of values. It's a specific type of message translator focused on harmonizing values rather than overall structure. Analogy: imagine a chef receiving ingredients with various measurements, cups, milliliters, ounces. The normalizer converts all these to a single, consistent unit like grams before the cooking process begins, ensuring the recipe works every time. How it works: the normalizer employs a set of rules or a lookup table to map incoming varying values to a predefined standard value. For example, any incoming gender value of M, male, 1, M would be translated to male. Use cases: standardizing date-time formats, e.g., converting all DDMMYYYY and MMDDYY to YYYYMMDD. Harmonizing product categories from different suppliers into a master product classification. Consolidating status codes from multiple transaction systems into a uniform success, failure, or pending status. Benefits: improves data quality and consistency, simplifies reporting and analytics across integrated data sources, and reduces the complexity of business logic in consuming applications as they only need to deal with standardized values. Conclusion: ensuring understanding. The transformation patterns: message translator, canonical data model, message enricher, and normalizer are indispensable tools in the integration developer's arsenal. They are the mechanisms that allow disparate systems to genuinely communicate, bridging the technical and semantic gaps that naturally arise in complex enterprises. By applying these patterns effectively, you ensure that messages are not just delivered to the right place, but that their content is always accurately understood, providing a foundation for reliable and meaningful business operations. In the next chapter, we will shift our focus to an equally critical aspect: ensuring the reliability and robustness of our integrated systems, even in the face of inevitable failures. Chapter 6. Ensuring reliability, error handling, idempotence, and durability. In the previous chapters, we've explored how messages are the lifeblood of integrated systems, how channels serve as their pathways, and how patterns help us route and transform them to ensure they reach the right place in the right format. This design enables systems to communicate effectively. However, in the realm of distributed systems, there's an undeniable truth: failures are inevitable. Networks cut out, servers crash, databases go offline, and code can have bugs. Relying on everything always working perfectly is a recipe for disaster. For an integration solution to be truly seamless, it must be resilient. It needs to anticipate, detect, and gracefully handle errors, ensuring that critical data is not lost and business processes operate correctly even when underlying components falter. This chapter introduces a set of patterns and concepts designed to build robust and trustworthy integration solutions, focusing on error handling, ensuring messages are processed correctly and only once, and maintaining data integrity. Guaranteed delivery, the promise of the message. Imagine sending an important legal document via postal mail. You wouldn't just drop it in a box and hope it gets there. You might send it certified mail, requiring a signature upon delivery, giving you assurance that it was received. In messaging, this concept is called guaranteed delivery. Guaranteed delivery means that a message sent by a producer will eventually reach its intended consumer, even if the producer, consumer, or the messaging system itself experiences temporary outages or failures. It's about persistence and reliability. Most modern messaging systems, like Kafka, RabbitMQ, ActiveMQ, AWS SQS, offer mechanisms for guaranteed delivery, typically by message persistence, storing messages on disk until they are successfully processed by the consumer. If the messaging system crashes, pending messages are not lost. Acknowledgements, AC case. The consumer explicitly tells the messaging system when it has successfully processed a message. Until an ACK is received, the message is retained by the messaging system and can be redelivered. Retries. If a consumer fails to process a message or doesn't send an ACK, the messaging system will redeliver the message after a delay. This leads to an at least once delivery guarantee. Understanding delivery guarantees, at most once, a message might be lost but will never be delivered more than once. Rarely desirable for critical business data. At least once. A message is guaranteed to be delivered, but it might be delivered multiple times. The common default for many robust messaging systems due to retries. This requires the consumer to be idempotent, exactly once. A message is delivered precisely one time. This is the holy grail, often achieved by combining at least once delivery with an idempotent consumer. True end-to-end exactly once semantics are very difficult to provide and are usually a composite of multiple patterns and careful system design. Understanding these guarantees is crucial because they dictate how you design your message consumers to handle potential duplicates. Idempotent consumer, processing messages reliably once. Given that, at least once, delivery is common, your message consumers must be designed to handle the possibility of receiving and processing the same message multiple times without causing incorrect results or side effects. This is the definition of an idempotent consumer. The problem: if a message is redelivered due to a network glitch, a consumer crash before ACKing, or a retry mechanism, and the consumer simply reprocesses it, it could lead to duplicate data creation, e.g., creating the same customer record twice. Incorrect financial transactions, e.g., charging a customer twice. Inconsistent state, e.g., incrementing a counter multiple times. The solution: an idempotent consumer can be executed multiple times with the same input without changing the result beyond the initial execution. It produces the same side effects, or lack thereof, every time. Analogy: pressing a light switch to on is generally idempotent. If the light is already on, pressing on again doesn't change its state, it just stays on. If it were not idempotent, pressing on again might break the bulb. How to achieve idempotence? Unique identifiers and deduplication. Every message, especially those representing an event or an action, should carry a unique identifier, often part of the correlation ID or a specific message ID. The consumer, before processing, checks if this ID has already been processed. If yes, it discards the message or acknowledges it immediately without reprocessing the business logic. This check often involves a database lookup or a distributed cache. Example: for an order payment message, the payment service checks if paymented XYZ has already been applied to an order. If so, it confirms success without attempting to charge again. Conditional updates. Instead of always setting a value, update it only if a specific condition is met, or increment it carefully. For example, use atomic database operations, update, set count equals count plus 1 where. State management. Design your systems to transition between well-defined states. An order might go from pending to processed. If a process order message arrives when the order is already in processed state, the consumer can ignore it. Version numbers optimistic locking. When updating records, include a version number and only apply the update if the current version matches the expected version. Implementing idempotence is a fundamental practice for building reliable systems on top of at least once messaging guarantees. Dead letter channel, handling the unprocessable. Not all messages can be successfully processed. Sometimes, a message is malformed, contains invalid data, or references non-existent records, preventing a consumer from ever being able to process it correctly. Retrying such a message endlessly would be futile and clog the system. The problem: a message, for various reasons, data corruption, schema mismatch, business rule violation, system bug, cannot be processed by any of its intended consumers. Continuing to retry, it consumes resources and can block valid messages. The solution: when a message cannot be processed after a configured number of retries, it is moved to a dead letter channel, also known as a dead letter queue or DLQ. This is a dedicated channel for poison pill or unprocessable messages. Analogy: imagine a sorting tray in a mailroom specifically for undeliverable mail. These aren't immediately discarded. They're set aside for human review to figure out what went wrong or if they can be salvaged. Purpose of a dead letter channel: isolation, prevents malformed messages from blocking the main processing flow. Diagnostics, provides a holding area for messages that need human intervention or further analysis to understand why they failed. This is invaluable for debugging and improving system robustness. Recovery, allows for manual reprocessing of messages after the underlying issue has been resolved, e.g., a bug fix deployed, missing data added. Auditing, serves as a record of failed processing attempts. Typical flow: consumer attempts to process a message. If processing fails, the message is typically redelivered by the messaging system up to n attempts. After n failures, the messaging system, or a dedicated error handler, diverts the message to the dead letter channel. An alert might be triggered for monitoring teams. Operators or developers can then inspect the DLQ, debug the issue, potentially correct the message data, and manually re-inject it into the main channel for reprocessing. Error handler, strategies for resilience. The dead letter channel is one part of a broader error handler strategy. An error handler defines how your integrated system responds to various types of failures. It's often a conceptual umbrella term encompassing retry policies, alternative paths, and notifications. The problem: how does an integration flow react when a service is unavailable, data is invalid, or an unexpected exception occurs during processing? A simple crash isn't acceptable. The solution: implement a robust error handling strategy. This involves retries. For transient errors, e.g., a temporary network glitch, a database timeout, the message processing can be retried. This is often done with a back-off strategy, waiting longer between attempts to avoid overwhelming the failing system. Circuit breaker, conceptual. If a downstream service consistently fails, an error handler might trip a circuit breaker, temporarily stopping further requests to that service to give it time to recover, preventing cascade failures. Messages can be queued or routed to an alternative path during this period. Alternative paths fallback. If a service is down or a specific processing step fails, can the message be handled by an alternative service or a human-driven process? Notifications and alerts. Instantly notify operations teams or logging systems about failures. This is crucial for proactive monitoring and rapid response. Logging and tracing. Log detailed information about failures, including message content, carefully, without sensitive data, error messages, and stack traces to aid in diagnosis. Compensating transactions for long-running processes. For multi-step transactions, if a later step fails, previous successful steps might need to be undone or compensated for. This is part of the saga pattern, which we'll touch on later. Effective error handling isn't just about catching exceptions. It's about designing a system that can gracefully degrade, recover, and provide visibility into problems without losing critical data. Competing consumers. Scalability with care. Modern systems often need to process high volumes of messages. One way to scale message consumption is by employing the competing consumers pattern. The problem: a single consumer might not be able to process messages fast enough, leading to message backlogs and delayed processing. The solution: multiple independent consumer instances listen to the same message channel, specifically, a point-to-point channel or queue. Each message is delivered to only one of the available consumers. This allows for parallel processing and load distribution. Analogy: several checkout lanes at a grocery store, all pulling customers from the same queue. Each customer goes through only one lane. How it works: the messaging system or its client library orchestrates the message delivery so that each message from the queue is given to one, and only one, active consumer. If a consumer crashes before acknowledging a message, the message is redelivered to another available consumer. Benefits: scalability, easily scale out message processing by simply adding more consumer instances. Load balancing. Messages are distributed across consumers, spreading the workload. Resilience. If one consumer instance fails, others can pick up the slack without service interruption. Implications for reliability. The competing consumers pattern inherently reinforces the need for idempotent consumers. Because messages are redelivered if a consumer fails, it's possible for the same message to be processed by different consumers at different times, but still only one at a time given a single active consumer. Without idempotence, this could lead to unintended side effects. Transactional client, ensuring atomicity in messaging. Ensuring atomicity, all or nothing, in distributed systems is notoriously difficult. However, messaging systems can play a crucial role in maintaining transactional integrity, particularly for operations that involve updating a database and publishing a message. The problem. Consider a service that updates a database record and then publishes a message, e.g., order processed or inventory level changed. If the database transaction commits but the message fails to send, or vice versa, the system can end up in an inconsistent state. The database is updated, but no one is notified, or a notification is sent for an update that never fully committed. The solution, conceptual. A transactional client ensures that the sending of a message is atomic with a local transaction, e.g., a database transaction. If the local transaction commits, the message is guaranteed to be sent. If the local transaction rolls back, the message is not sent. How it's often achieved, without proprietary distributed transactions that tie systems too tightly. Transactional outbox pattern. This is a common and robust pattern. Instead of directly sending a message to a message broker, the application first records the outgoing message in a dedicated outbox table within the same database transaction as the business data update. If the database transaction commits, both the business data change and the pending outgoing message are committed atomically. A separate relayer process then monitors this outbox table, sends the messages to the actual message broker, and marks them as sent. If the relayer fails, the outbox entries remain, ensuring no message is lost. If the relayer sends duplicates, the consumer relies on idempotency. Messaging system transactions, less common, more complex. Some messaging systems support transactional operations where sending and receiving messages can be part of a larger transaction managed by the messaging system itself. However, these are often limited in scope. The transactional outbox pattern is a powerful way to provide atomicity between database operations and message publishing, serving as a robust transactional client implementation. Conclusion: building trust in your systems. Building reliable integration solutions is not about avoiding failures entirely. It's about expecting them and designing for them. The patterns and concepts discussed in this chapter, guaranteed delivery, idempotent consumers, dead letter channels, sophisticated error handler strategies, competing consumers for scale, and transactional clients for atomicity, are crucial for creating systems that are resilient, maintain data integrity, and can recover gracefully from adverse conditions. By embracing these principles, you move from brittle connections to robust, trustworthy, seamless systems that continue to function dependably even amidst the chaos of distributed computing. In the next chapter, we'll explore patterns related to managing and synchronizing data across integrated systems. Chapter 7: Managing State and Context Data Integration Patterns. In previous chapters, we laid the groundwork for messages flowing through channels, routed to the right places, transformed into usable formats, and handled reliably even in the face of failure. But integration often goes beyond simply moving data. It involves managing the state of shared information across multiple independent systems. How do we ensure that when a customer's address changes in one system, that change is accurately reflected in others? How do we trace a single business transaction across a dozen services? And how do we gain visibility into the complex flows of data? This chapter delves into patterns that address these challenges, focusing on how different systems can maintain a consistent view of shared data, trace the journey of a request or event, and enable centralized monitoring and management. We'll explore traditional approaches and modern solutions for data integration. The challenge of shared state in distributed systems. In monolithic applications, data consistency is often managed through tightly coupled transactions within a single database. When you break down a monolith into microservices or other distributed systems, each service typically owns its own data. This is great for autonomy and scalability, but it introduces a fundamental challenge. How do you ensure consistency and accuracy when the truth about a customer, product, or order is scattered across different databases owned by different services? Simple replication or direct database access can quickly lead to tight coupling, performance bottlenecks, and a lack of clear ownership. The goal of data integration patterns here is to facilitate the sharing and eventual consistency of data without compromising the autonomy and scalability benefits of distributed architectures. Database integration patterns: when and why not? Historically, some integration strategies relied directly on shared databases. While tempting for their apparent simplicity, they often introduce significant coupling. 1. Shared database. The problem: multiple applications need to access and update the same business data, e.g., customer records, product catalog. The solution: all applications directly access and share a single database instance. Analogy: a single, large filing cabinet in the middle of an office that everyone uses directly, adding, removing, and updating files as needed. Why it's used appears straightforward for small teams or tightly coupled applications. Common in earlier monolithic patterns where different modules of the same application might access the same database. Why it's often an anti-pattern in distributed systems. Tight coupling. Applications are tightly coupled to the database schema. A change in one application's ORM or query heavily impacts others. Scalability bottlenecks. The single database can become a performance bottleneck. Technology lock-in. All applications must use compatible database technologies and drivers. Data conflicts. Ensuring consistency, e.g., through proper locking and transactions, across truly independent applications when they simultaneously update the same rows can be a nightmare. Lack of ownership. No clear owner for the data and its schema, leading to lowest common denominator design. In a microservices world, the shared database is largely avoided. Each service should own its data and expose it through well-defined APIs or events, rather than direct database access. Too common database, less common today. The problem: similar to shared database, but perhaps for more batch-oriented or data warehousing scenarios where a reconciled, integrated view of data is needed. The solution: data from various source systems is regularly extracted, transformed, and loaded ETL into a central, dedicated database, the common database. Other applications or reporting tools then query this common database. Analogy: instead of everyone using the same live filing cabinet, each department keeps its own records. Periodically, a dedicated clerk collects all records, standardizes them, and files them into a central, read-only archive cabinet for anyone to consult. Use cases: data warehousing, business intelligence, reporting, and certain types of master data management. It's often used for analytical purposes rather than real-time transactional updates. Trade-offs: data can be eventually consistent, not immediately up-to-date, requires complex ETL processes, still carries some complexity in schema design. While these database-centric patterns have their niche, modern integration heavily favors patterns that promote looser coupling and data ownership, often relying on messaging and event-driven architectures. Reliable data propagation, the transactional outbox pattern. As hinted in Chapter 6, the transactional outbox pattern is a powerful modern technique for reliably publishing data changes from a service's internal database to a messaging system, ensuring atomicity between the database update and the message publication. The problem: how can a service ensure that when it successfully commits a change to its database, e.g., order status updated, a corresponding message or event reliably makes it to the message broker for other services to consume? A naive approach: commit to DB, then send message, risks inconsistency if the message send fails. Distributed transactions are complex and lead to tight coupling. The solution: instead of sending the message directly to the message broker, the service records the outgoing message in a dedicated outbox table within the same database transaction as the business data change. Atomic right. The service updates its business data and inserts the message into its outbox table or similar in a single atomic database transaction. If the transaction commits, both are saved. If it rolls back, neither is. Message relayer. A separate, independent process, the relayer or outbox publisher, periodically scans the outbox table for new, unsent messages. Send and mark. The relayer reads messages from the outbox, sends them to the external message broker, and then marks them as sent in the outbox table. Benefits: guaranteed consistency. Ensures that a business operation is either fully committed, including the event for others, or fully rolled back. Loose coupling. The service's core business logic doesn't need to know about the message broker details. Resilience. If the message broker is down, the relayer simply stops sending, but no data is lost from the outbox. It retries when the broker becomes available. Scalability. The relayer can be scaled independently of the main service. Considerations. Adds a slight delay before messages appear on the broker, requires consumers to be idempotent, as the relayer might send duplicates if it crashes after sending, but before marking as sent, and needs monitoring for the relayer process. This pattern is a cornerstone for building robust event-driven microservices that reliably propagate their state changes. Tracing the flow, correlation identifier. When a single business transaction spans multiple services and messages, understanding its complete lifecycle, from initial request to final completion, can be incredibly challenging without proper tools. The correlation identifier provides the conceptual glue. The problem: in deeply integrated systems, a single business transaction might involve a request moving through an API gateway, then triggering a chain of messages between a payment service, an inventory service, a fulfillment service, and a notification service. If something goes wrong in the middle of this chain, it's difficult to trace the entire journey and pinpoint the source of the issue. The solution: a unique correlation ID is generated at the very beginning of a business transaction and then passed along in the header of every message, request, or event related to that transaction as it flows through the integrated system. Analogy: a police case number. From the initial report to evidence, lab results, court proceedings, and final verdict, every document related to that case is stamped with the same unique number. If you need to understand the whole story, you just follow the case number. How it works: generation. The originating system, e.g., the mobile app, the API gateway, the initial service generates a unique ID, e.g., a UUID or GUID. Propagation. This correlation ID is then included in the message header of every subsequent message, event, API request, or log entry related to that specific transaction. Tracing. Centralized logging and monitoring systems can then aggregate and display all log entries and messages that share the same correlation ID, allowing developers and operations teams to reconstruct the entire execution flow of a single business transaction. Benefits: debugging. Drastically simplifies debugging and troubleshooting in distributed systems. Monitoring enables the monitoring of end-to-end transaction latency and success rates. Auditing provides an auditable trail of events related to a specific business transaction. Considerations: requires consistent implementation across all services and components. Ensure the ID is always passed along, and logs are enriched with it. Gaining visibility, the control bus. Managing a complex integration landscape requires more than just individual messages flowing reliably. You need a way to monitor the health of your integration components, configure them, and potentially even dynamically change their behavior. This is where the concept of a control bus emerges. The problem: distributed integration systems comprised of many independent components can be difficult to manage. How do you monitor their heartbeat, update their configuration without downtime, or collect diagnostic information from them centrally? The solution: a control bus is a dedicated message channel, often a publish-subscribe channel, used specifically for sending control messages to and receiving monitoring data from integration components. It separates management communication from business data communication. Analogy: in a smart home, the regular electrical wiring carries power for lights and appliances. But there's also a separate control network, e.g., Zigbee Z-Wave, that lets your smart hub send on-off commands to lights, receive door open, status from sensors, and update thermostat settings. How it works. Monitoring data. Integration components, e.g., routers, transformers, endpoints, publish their status, performance metrics, and diagnostic information to the control bus. Configuration updates. Centralized management tools send configuration messages, e.g., change a routing rule, adjust a throttling limit, over the control bus to specific components. Logging commands. Commands can be sent to adjust logging levels on the fly. Benefits. Centralized management provides a single point for managing and monitoring a distributed integration infrastructure. Operational visibility. Real-time insight into the health and performance of your integration components. Dynamic configuration allows for runtime changes without redeploying components. Separation of concerns. Business logic and management logic are cleanly separated. Implementation. Often built on top of the same messaging infrastructure, e.g., a dedicated Kafka topic or RabbitMQ exchange for control messages, but with distinct message types and access controls. Event sourcing, conceptual, state as a stream of events. While not strictly an integration pattern, in the EIP original sense, event sourcing is a powerful pattern for state management in distributed systems that inherently generates events ripe for integration. The problem: traditional database systems store the current state, e.g., the current balance of an account. To understand how that state was reached, you'd typically look at update and delete commands, which often lose historical context. In distributed systems, replicating and synchronizing current state across many services can be complex and error-prone. The solution: instead of just storing the current state, event sourcing stores a complete, ordered sequence of immutable events that happen to an entity. The current state is then derived by replaying these events from the beginning. Analogy: instead of a bank account just showing your current balance, think of it as a ledger that records every deposit and withdrawal. Your balance is simply the sum of all entries in the ledger. The ledger itself is the source of truth, and your current balance is just a projection. How it applies to integration. Every change to a system state is an event, e.g., order created, item added to order, payment received. These events are typically published to a central append-only log, like Kafka or a dedicated event store. Other services can then subscribe to these event streams and build their own read-optimized projections or react to specific events without directly querying the source service's database. This naturally promotes loose coupling and an event-driven architecture. Benefits: auditing and debugging. A complete history of changes is available. Temporal queries: you can reconstruct the state of an entity at any point in time. Natural events for integration. The core business logic naturally produces events that can be consumed by other services. Loose coupling. Services interact via events, eliminating direct API calls for state synchronization. Conclusion: synchronized, traceable, and observable. Managing shared state and gaining operational insight are paramount in complex distributed environments. While direct database sharing should generally be avoided, patterns like the transactional outbox provide robust mechanisms for propagating data changes reliably. The correlation identifier is your indispensable tool for tracing transactions across a web of services, and the control bus offers a dedicated channel for monitoring and managing your integration landscape. Furthermore, architectural approaches like event sourcing fundamentally shift how state is managed, inherently generating granular events that fuel powerful, loosely coupled integrations. By skillfully applying these patterns, you move from individual components to a cohesive system where data integrity is maintained. Problems can be quickly diagnosed, and operational health is clearly understood. In the next chapter, we'll continue our journey, moving beyond foundational patterns to explore how to handle complexity with higher-level command and event patterns that coordinate sophisticated business processes. Chapter 8. Beyond the core, handling complexity with command and event patterns. Up to this point, our journey through enterprise integration patterns has focused on the fundamental mechanics, getting messages from point A to point B, ensuring they are understood, and handling inevitable failures. We've equipped ourselves with a toolkit for reliable data movement and transformation. Now, it's time to elevate our perspective and look at how we coordinate complex business processes that span multiple, decoupled services. This chapter introduces patterns that deal with the intent of communication and the facts that emerge, enabling sophisticated workflows and ensuring consistency across distributed systems. The language of systems: commands, events, and queries. In a distributed environment, services communicate for different reasons. Understanding the nature of these communications is crucial for designing robust and maintainable systems. Let's formalize the three primary types of messages that drive interactions between services. Commands: nature, a request to do something. It's imperative, stating an intention or an action to be performed. Characteristics: intentional. Please process this order. Please update that customer record. Single recipient: typically. Commands usually target a specific service or component that is responsible for executing that particular action. Expected side effect: a command is meant to cause a change in the state of the system. Failure potential: commands can fail if the conditions for their execution are not met, e.g., insufficient funds, product out of stock. Analogy: giving a direct, explicit instruction to a specific person. John, please compile this report by 5 p.m. Events: nature, a notification that something has happened and is a statement of fact in the past tense. Characteristics: statement of fact, order was placed, payment failed, inventory was updated. Multiple potential recipients: events are usually broadcast. Any service interested in that particular fact can react to it. The publisher of the event typically has no knowledge of who or how many consumers will react to it. No direct side effect for publisher. Publishing an event doesn't change the state of the system that published it. It merely announces a fact about its state. Consumers might react with their own side effects. Immutable: once an event has occurred, it cannot be undone or changed. It's a historical record. Analogy: making an announcement to a general audience. The train has arrived at platform 3. Anyone listening can decide how to react to this information. Queries: nature, a request for information. Characteristics: read-only. Queries do not cause any side effects or change the state of the system. Information retrieval: what is the status of order X? Get me the details of product Y. Analogy: asking a question. Could you tell me what time the store closes? Choosing whether to use a command or an event for communication significantly impacts service coupling. Commands lead to a more request-driven, often synchronous interaction. Events promote a highly decoupled, asynchronous, and reactive style of integration, allowing systems to independently react to changes. The messaging backbone: command bus fees. Event bus. These distinct communication types often live on different messaging infrastructure paradigms, forming a command bus and an event bus. Command bus. Purpose: to reliably deliver a command message from its sender to its single, intended recipient. Underlying EIP: typically built upon a point-to-point channel, like a message queue. A command is sent to a queue, and a specific service processes it. If multiple instances of that service are running, they compete to consume messages from the queue via the competing consumer's pattern. Interaction model: one-way request, often with an eventual acknowledgement or response to a different channel. Analogy: a centralized work assignment desk distributing tasks to specific teams. Event bus. Purpose: to broadcast events to all interested subscribers. Underlying EIP: typically built upon a publish-subscribe channel, like a message topic or stream. An event is published on a topic, and all subscribers to that topic receive a copy. Interaction model: fire and forget. The publisher doesn't care who consumes the event or what they do with it. Analogy: a public announcement system or newswire, broadcasting information that anyone can tune into. Many complex systems utilize both a command bus for specific actions and an event bus for broadcasting facts, allowing for a hybrid approach to interaction. CQRS: separating reads from writes. The distinction between commands and queries leads naturally to a powerful architectural pattern called command-query responsibility segregation, CQRS. The problem: in many applications, the logic for updating data, handling commands, and the logic for reading data, handling queries, have very different requirements. Write operations might need strong consistency and complex validation. Read operations might need high performance, denormalization for faster querying, and support for complex filtering searching. Trying to optimize a single data model for both can lead to compromises on both sides. The solution: CQRS separates the model used for updating information, the write model or command side, from the model used for reading information, the read model or query side. How it works: conceptual flow. A command, e.g., place order, is sent to the write model. The write model processes the command, potentially performing validations and applying business logic, then updates its backend data store, e.g., a traditional relational database. Crucially, after successfully updating its state, the write model publishes one or more events, e.g., order placed, inventory reserved, reflecting the state change. This often leverages the transactional outbox pattern from Chapter 7 for reliability. A separate part of the system subscribes to these events. It consumes the events and uses them to update a read model, which is specifically designed and optimized for querying, e.g., a NoSQL database, a search engine index, a materialized view in a relational database. Queries are then directed to the read model, which can be highly optimized for read performance, denormalized, and even eventually consistent, independently of the write model's requirements. Analogy: think of a restaurant. The kitchen right side is optimized for taking orders, preparing food, and managing inventory. Its internal data structures are about ingredients, recipes, and tasks. The menu read side is what customers see. It's optimized for browsing, with dish descriptions and prices, but it's not where the cooking happens. Changes in the kitchen, e.g., chef invents a new dish, eventually get reflected on the menu. Integration relevance. CQRS heavily relies on the command and event messaging patterns. Commands drive the write side, and events propagate state changes from the write side to keep the read side eventually consistent. Benefits: scalability. Read and write sides can be scaled independently based on their load. Optimized models. Each side can use the data model and storage technology best suited for its purpose. Flexibility. Easier to adapt to evolving business requirements for both transactions and reporting. Considerations: adds significant complexity, introduces eventual consistency for reads, and requires careful event design and data synchronization logic. It's often reserved for complex domains where its benefits outweigh the added architectural overhead. The saga pattern: coordinating distributed transactions. One of the most challenging aspects of distributed systems is maintaining data consistency and transactional integrity across multiple services, each owning its own data. Traditional two-phase commit 2PC protocols, common in older monolithic distributed transactions, are generally avoided in modern microservices architectures because they introduce tight coupling, complex failure modes, and performance bottlenecks. The saga pattern provides an alternative. The problem: a business process, like placing an e-commerce order, often involves multiple steps that update data in different services. For example, deduct payment from customer payment service, check and reserve inventory service, create shipping manifest shipping service. If any step fails, how do you ensure that all previous successful steps are undone or compensated for, maintaining a globally consistent state? The solution: a saga is a sequence of local transactions, where each local transaction updates data within its own service and then publishes an event that triggers the next step of the saga. If a local transaction fails, the saga executes a series of compensating transactions to reverse the changes made by previous successful steps, achieving eventual consistency and rolling back the overall business process. Key principles: each step is a local ACID transaction within a single service. Communication between saga participants is asynchronous via events and commands. Rollback is achieved through compensating actions, not technical rollback. 2 primary saga orchestration styles: choreography, decentralized saga. How it works: each service involved in the saga participates by performing its local transaction and then publishing an event. Other services, which are interested in that event, react by executing their own local transactions and publishing new events, thereby chaining the process. There is no central coordinator. Analogy, a flash mob. Each dancer knows their unique part and how to react to cues from other dancers to keep the performance going. Pros: highly decentralized, loose coupling between participants, simpler to implement for simple sagas. Cons: harder to monitor the overall progress of the saga, complex error handling, as failure recovery logic is distributed, potential for circular dependencies if not carefully managed. Orchestration, centralized saga. How it works. A dedicated saga orchestrator, which is typically a separate service, manages the entire workflow. The orchestrator receives the initial command, sends commands to each participant service in turn, and waits for their responses events. It then decides the next command to send. If a participant indicates failure, the orchestrator issues compensating commands to previously successful participants. Analogy: a theater director guiding actors through a play. The director tells each actor when to speak their lines or perform an action, knowing the entire script. If an actor forgets their line, the director can intervene and correct the flow. Pros: centralized control over the workflow, easier to monitor and manage, clearer separation of business logic from coordination logic, easier to implement compensating actions. Cons: the orchestrator can become a single point of failure, though this is typically addressed with high availability and persistence. More coupling between the orchestrator and participant services, though still loose compared to 2PC. Compensating transactions. These are the undo actions. If an order process fails at the shipping step, the compensating transaction for the payment step might need to refund the customer, and for inventory, it might need to unreserve the stock. Designing these compensation steps is critical for a robust saga implementation. Integration relevance. Sagas are prime examples of how command and event messages, coupled with the reliability patterns, guaranteed delivery, idempotent consumers, transactional outbox, are used to achieve complex business process consistency in distributed systems. Conclusion: orchestrating sophisticated workflows. The patterns discussed in this chapter, the precise distinction and application of commands, events, and queries, the architectural separation of CQRS, and the distributed transaction coordination of the saga pattern, signify a move beyond mere data exchange to the orchestration of complex business logic across independent systems. They address the intricacies of state consistency and workflow management in environments where traditional monolithic approaches fall short. By mastering these patterns, developers can design highly scalable, resilient, and business-aligned integrations that truly reflect the dynamic nature of modern enterprises. In the next chapter, we will bridge these foundational and advanced patterns with the realities of contemporary architectural styles like microservices, APIs, and broader event-driven systems. Chapter 9. The Modern Integration Landscape, APIs, Microservices, and Event-Driven Architectures. We've covered a lot of ground, delving into the foundational building blocks of messages, channels, and endpoints, and then examining patterns for routing, transforming, and ensuring the reliability of our integrated systems. We've even ventured into the complex world of coordinating distributed transactions. Now, it's time to connect these timeless integration patterns to the architectural styles that dominate today's software development: microservices, APIs, and event-driven architectures. You'll see that the enterprise integration patterns are not just historical artifacts. They are the underlying principles that make these modern systems work, often acting as the silent orchestrators behind the scenes. EIPs in the microservices era. The microservices architectural style advocates for building applications as a collection of small, autonomous services, each owning its data and communicating via well-defined interfaces. While microservices offer unprecedented agility, scalability, and resilience, they inherently introduce a significant integration challenge. How do hundreds or thousands of these small, independent services communicate effectively and reliably? This is where EIPs become indispensable, providing the conceptual blueprint for inter-service communication. The API gateway, your smart front door. In a microservices architecture, Clients, web browsers, mobile apps rarely call individual microservices directly. Instead, they interact with an API gateway. This EIP is essentially a specialized message gateway with added intelligence. Role: the API gateway acts as a single, unified entry point for all external requests. It receives requests from clients and routes them to the appropriate backend microservices. EIP manifestations: message gateway/message router. Its core function is to route incoming requests to the correct internal service, often using parameters in the request, like URL paths or headers, as criteria. Message enricher: it can transform requests, add authentication or authorization headers, e.g., adding user identity after validating a token, or enrich the request with other context before forwarding it to a service. Message filter: it can perform rate limiting, block malicious requests, or apply access control policies, filtering out unauthorized or excessive traffic. Splitter implicitly: for complex UI requests that require data from multiple services, the API gateway might fan out requests to several services and then aggregate their responses before sending a single, consolidated response back to the client. This is a form of scattergather. The API gateway centralizes concerns like security, rate limiting, logging, and routing, preventing each individual microservice from having to implement these cross-cutting functionalities. Service mesh: the invisible integration layer. As microservice deployments grow, managing inter-service communication can become complex. This led to the rise of the service mesh. A service mesh, like Istio, Linkerd, isn't a single product but an infrastructure layer that handles service-to-service communication within a microservices application. It typically involves a sidecar proxy running alongside each service. Role: the service mesh abstracts away complex network functions from the application code. It ensures reliable delivery of messages between services. EIP manifestations: message router. The service mesh automatically routes requests between services, handling service discovery and load balancing. Error handler/circuit breaker. It implements retry logic, timeouts, and circuit breaking patterns, as discussed in Chapter 6, at the network layer, making inter-service calls more resilient without the application developer worrying about it. Control bus for observability. It captures rich telemetry and metrics, like request counts, latency, error rates, for every service call, feeding into centralized monitoring systems, providing a control plane for the entire mesh. Message filter/content-based router. It can apply traffic policies, such as routing a percentage of traffic to a new version of a service for A/B testing or canary deployments, based on request content or headers. The service mesh effectively provides a robust, intelligent messaging toolkit between services, offloading many of the EIP implementations from the application developer to the infrastructure layer. Event-driven architectures, EDA. The EIP heartbeat. Event-driven architectures are a fundamental component of modern distributed systems, and they are inherently built upon enterprise integration patterns, particularly those related to messaging. Concept. In an EDA, services communicate by publishing events, facts about something that happened, in the past tense, to an event bus, a specialized publish-subscribe channel like Apache Kafka, RabbitMQ, or cloud-native services. Other services that are interested in those events subscribe to the bus and react asynchronously. Core EIPs in EDA, publish-subscribe channel. This is the absolute backbone of almost all EDAs. Producers publish once, and all interested consumers receive a copy. Event message, the primary unit of communication. As discussed in Chapter 8, events are immutable and merely state that something has occurred. Event source revisited. When a service uses event sourcing, Chapter 7, its internal state changes are recorded as a stream of events. These events are then published to the event bus, making the service a natural event producer for the broader system. Message filter/content-based router. For consumers. Consumers of events often don't care about all events. They subscribe to a topic, but then internally use a message filter or a content-based router to process only the events relevant to their specific business logic, e.g., only process order-placed events where product category is books. Message translator/normalizer. Events might originate from different systems with varying internal representations. An EDA often employs message translators or normalizers to ensure events conform to a common, understandable schema before being consumed by multiple services, fostering semantic interoperability. Correlation ID, crucial for tracing the flow of events across multiple services. If an initial event triggers a chain of subsequent events, e.g., order placed, payment processed, shipping label generated, the correlation ID allows you to reconstruct the entire sequence. Saga choreography. As explored in Chapter 8, the choreography style of the saga pattern is a perfect fit for EDAs. Services execute their local transactions and publish events that implicitly trigger the next step in the distributed business process without a central orchestrator. Benefits of EDA: extreme decoupling. Publishers and subscribers have minimal knowledge of each other. Producers don't know who consumes their events, and consumers don't know where events originated. High scalability. Components can scale independently based on their load. Resilience. If a consumer is temporarily down, events simply queue up on the bus and wait for it to recover. The producer remains unaffected. Real-time reactions. Enable systems to react to changes as they happen. Challenges of EDA: eventual consistency. Data across services might not be immediately consistent. Debugging complexity. Tracing faults and understanding the flow through an asynchronous event chain can be challenging without good tooling, e.g., distributed tracing with correlation IDs. Synchronous versus asynchronous communication. Choosing the right tool. One of the most common design decisions in modern integration is whether to use synchronous or asynchronous communication. Both are vital, and EIPs exist to support both. Synchronous communication, e.g., REST-TFL APIs, concept. A client sends a request and immediately waits for a response, similar to a traditional function call. EIPs. The interactions typically embody the request-reply pattern. The API gateway acts as a message gateway. When to use, immediate response is required, e.g., UI needs to display result to user instantly. Simple request-response interactions. Strong consistency is critical within the bounded context of the immediate request. Pros: simpler to understand and implement for basic interactions, immediate feedback for the caller. Cons: tightly coupled, caller is directly dependent on the availability and responsiveness of the CALI. Blocking calls, harder to handle failures gracefully, can create cascading failures if services are unavailable. Asynchronous communication, e.g., messaging events, concept. A client producer sends a message and continues its processing without waiting for an immediate response. Another system, consumer, processes the message later. EIPs. Leverages point-to-point channels for commands tasks and publish-subscribe channels for events, often using message endpoints. When to use, decoupling services for independent evolution and scaling. Long-running processes, e.g., order fulfillment. Broadcasting facts, events to multiple interested parties, when high throughput and resilience are priorities. Pros: loose coupling, high scalability, improved resilience, producer is not blocked by consumer availability. Allows for fire and forget and eventual consistency. Cons: higher complexity in debugging. Eventual consistency requires careful design, managing distributed transactions with patterns like Saga. The best modern solutions often use a blend of both, leveraging synchronous APIs for immediate, interactive needs and asynchronous messaging events for background processing, long-running workflows, and propagating state changes across the system. Serverless functions and integration patterns. Serverless computing, e.g., AWS Lambda, Azure Functions, Google Cloud Functions, has gained immense popularity. What's often overlooked is that serverless platforms are fundamentally event-driven and directly embody many EIPs. Concept: developers write small, single-purpose functions that are automatically triggered by specific events, e.g., a message arriving in a queue, a file being uploaded to storage, an HTTP request. You only pay for the compute time used by the function. EIP manifestations, message endpoints. Serverless functions often act as message endpoints, implicitly designed to respond to messages events from various sources, queues, topics, databases, HTTP requests, pipes, and filters. Complex workflows in serverless often string together multiple functions, where one function processes input and passes it to another via an external channel, e.g., function A processes data, drops a message into a queue, function B picks it up. This forms a direct implementation of the pipes and filters metaphor. Message transforms/enrich. Functions are perfect for performing granular message transformations or enrichments, taking an input message, modifying, adding data, and passing it along. Control bus via cloud monitoring. Cloud providers build extensive monitoring and logging around serverless functions, effectively providing a control bus to observe their execution, errors, and performance. Cloud-native messaging services, like AWS SQS SNS Event Bridge, Azure Service Bus Event Grid, GCP PubSub, are essentially highly managed, scalable implementations of message channels and message routers, directly supporting these EIPs within the serverless paradigm. Hybrid cloud and multi-cloud integration challenges. As enterprises increasingly adopt cloud strategies, integration challenges extend beyond a single data center or cloud provider. Hybrid cloud combines on-premises systems with public cloud resources, while multi-cloud involves using services from more than one public cloud provider. Challenges: network latency across different environments, differing security models, data governance boundaries, vendor lock-in concerns, and tool sprawl. How EIPs help: by abstracting communication through generic concepts like messages and channels, EIPs promote location independence. They encourage loose coupling, meaning services are less concerned with where another service is running, as long as it can receive messages to from a defined channel. Federated message brokers. Concepts like federated message brokers, e.g., RabbitMQ shovels, Kafka Mirror Maker, allow for channels to span across different data centers or cloud regions, enabling messages to flow seamlessly. API gateways can span environments to provide a unified access layer. Canonical data models become even more critical to ensure data consistency across diverse environments. EIPs integration platform as a service. Cloud-native EIPs solutions provide managed services that encapsulate many EIPs, offering connectors and orchestration capabilities to integrate applications both within and across cloud boundaries. Conclusion: EIPs, the timeless language of modern systems. Whether you're building a highly distributed microservices platform, embracing an event-driven architecture for real-time reactivity, or leveraging the power of serverless computing, the enterprise integration patterns are the conceptual bedrock. They provide the fundamental vocabulary and proven solutions for how independent software components can communicate, coordinate, and maintain integrity in complex, distributed environments. From the macro-level design of an API gateway or service mesh to the granular understanding of how an event message drives an EDA, EIPs are continually being rediscovered and re-implemented in new technologies and frameworks. They are not just patterns from a book. They are the timeless principles guiding the construction of current and future seamless systems, ensuring that our ever-growing digital ecosystems can truly work in harmony. In the next chapter, we'll translate this understanding into actionable design principles and strategic considerations for building robust integrated systems. Chapter 10. Designing integrated systems, principles, styles, and strategic implementation. Having explored the diverse catalog of enterprise integration patterns, from the atomic message to complex saga coordination, you now possess a powerful toolkit. However, knowing the tools is only half the battle. The true artistry lies in knowing when to use which tool, how to combine them, and how to integrate them into a cohesive, maintainable, and evolving architectural strategy. This chapter shifts our focus from the what and how of individual patterns to the why and when of overall system design, covering various integration styles, strategic decisions, core design principles, and operational considerations. Integration styles revisited, choosing the right approach. Before diving into specific patterns, it's essential to understand the overarching strategies, or styles, for connecting disparate systems. Each style has its strengths and weaknesses, making it suitable for different contexts and requirements. File transfer. Description. Systems exchange data by writing to and reading from shared files, e.g., CSV, XML, JSON files deposited in a shared folder, FTP server, or cloud storage bucket. When to choose. For batch processing where latency is not critical, exchanging large volumes of data infrequently, or when integrating with legacy systems that only support file-based exchanges. Pros. Simple to implement initially, low technical barrier, widely supported. Cons. Not real-time, often lacks strong guarantees, guaranteed delivery, and transactional integrity. Error handling can be complex, difficult to monitor data flow. Highly coupled through file format and location. EIPs at play, primarily file transfer, perhaps with message translator if file formats differ, and message filter for specific record types. Shared database. Description. Multiple applications directly access and modify data in a common database. When to choose. Almost never for new distributed systems or microservices. It's often an anti-pattern for loose coupling, though it might persist in some legacy monolithic architectures where internal modules share a database. Pros. Appears simple for tightly coupled components within a monolithic application. Cons. High coupling, scalability bottlenecks, technology lock-in, data consistency issues without strong transactional guarantees across applications, difficult to evolve schema. EIPs at play. Conceptually the shared database pattern, but often leading to integration spaghetti at the data layer. Remote procedure invocation, RPC/API calls. Description. One system makes a direct, synchronous request to another system's exposed service, e.g., REST APIs, gRPC. The caller typically waits for an immediate response. When to choose. For real-time, request-response interactions where the caller requires an immediate result. Common for user-facing applications, e.g., mobile app calling a backend API. Pros. Intuitive programming model, like calling a local function, immediate feedback, widely supported with standard protocols, HTTP/TCP. Cons. Tight coupling, caller directly depends on Kali's availability and responsiveness. Blocking calls can reduce throughput, difficult to handle network latency and transient failures gracefully. Brittle API contracts can lead to synchronous cascades on failure. EIPs at play, primarily the request-reply pattern. An API gateway acts as a complex message gateway and content-based router. Messaging. Description. Systems exchange discrete, self-contained messages via an intermediary message broker or message queue, promoting asynchronous communication. When to choose. For highly decoupled systems, long-running processes, event-driven architectures, situations requiring high scalability and resilience, and integrating many-to-many systems. Pros. Loose coupling, high scalability, producers and consumers scale independently. High resilience messages persist even if consumers are down, supports complex asynchronous workflows, sagas, enables eventual consistency. Cons. Increased complexity, asynchronicity, idempotence, eventual consistency, harder to debug and trace flows without proper tooling, requires a message broker infrastructure. EIPs at play. All other patterns discussed in this book are primarily built upon the messaging style. Messages, channels, point-to-point, publish-subscribe, endpoints, routers, transformers, aggregators, sagas, etc. Choosing the right style. Latency. Do you need real-time RPC messaging, or can it be batch file transfer? Coupling. How much dependency are you comfortable with between systems? Messaging offers the loosest. Scalability and resilience. How critical is it for systems to operate independently and survive failures? Messaging provides the highest resilience. Complexity. Simple point-to-point RPC might be easier initially, but messaging patterns scale better for complex ecosystems. Data consistency. Immediate RPC, often within one service's domain, or eventual messaging for cross-service consistency. A modern enterprise typically employs a hybrid approach, using synchronous APIs for immediate interactive experiences and asynchronous messaging for background processing, event propagation, and internal system coordination. Strategic implementation, build versus buy. Once you select an integration style, a crucial decision is whether to custom build your integration components or leverage commercial off-the-shelf. COTS, products and platforms. Build custom development. Pros, full control, tailored precisely to your unique business requirements. No vendor lock-in, you own the code and technology stack. Cost-effective for simple cases. Initial development costs might be lower for very specific, simple integrations. Deep integration can integrate very closely with internal systems that might lack standard interfaces. Cons, high development and maintenance cost. Requires skilled developers, ongoing maintenance, bug fixes, and upgrades. Time-consuming, slower time to market, especially for complex integrations. Reinvention of the wheel often means building functionalities that already exist in market products, e.g., routing, transformation engines, retry logic. Requires expertise, needs deep knowledge of EIPs, distributed systems, and messaging. Buy commercial products, EIPs, ESB. Commercial ESBs, enterprise service buses. Traditional heavyweights, e.g., TIBCO, MuleSoft Endpoint Platform, IBM Integration Bus. They offer comprehensive features like routing, transformation, protocol mediation, monitoring, and security. EIPs Integration Platform as a Service. Cloud-native, subscription-based platforms e.g., MuleSoft Endpoint, Dell Boomi, Workato, Azure Integration Services, AWS Step Functions, EventBridge. They provide managed services for API management, messaging, ETL, and serverless orchestration. Pros, faster time to market. Pre-built connectors, visual designers, and managed services accelerate development. Reduced development burden, offloads infrastructure, maintenance, and complex EIP implementation to the vendor. Managed services. Vendors handle scaling, security patches, and upgrades. Comprehensive features often include advanced monitoring, governance, and analytics out of the box. Cons, vendor lock-in. Migrating away from a platform can be challenging. Licensing costs can be significant, especially for large enterprises. Configuration versus coding. While less code requires significant configuration and understanding of the platform. Monolithic ESB risk. Centralized ESBs can become bottlenecks and single points of failure if not well architected. EIPs mitigates this risk through distributed, serverless components. Strategic guidance. For specialized, performance-critical, or truly unique integration needs, building might be justified. However, for common system-to-system integrations, SaaS application connectivity, and enterprise-wide data movement, buying an EIPs solution often provides a faster, more robust, and more cost-effective path by leveraging best-of-breed EIP implementations and managed services. Core design principles for robust integration. Beyond specific patterns and styles, several overarching principles should guide all integration design decisions. Loose coupling. Definition. Systems should be able to operate, evolve, and fail independently without tightly impacting other systems. Application. Embrace asynchronous messaging, publish subscribe channels primarily over synchronous calls where possible. Use well-defined, stable API contracts. Avoid shared databases. Services should only know about the interfaces of other services, not their internal implementations. Why it matters. Increases agility, resilience, and scalability. Reduces the integration spaghetti. High cohesion/single responsibility. Definition. Each integration component, e.g., a message translator, a part of a router, a microservice, should have a single, well-defined responsibility. Application. Design services and integration components to do one thing well. Avoid God services or smart ESBs that try to do too much. Split complex transformations or routing logic into smaller, focused components. Why it matters. Enhances clarity, reusability, testability, and maintainability. Bounded contexts. Definition. From domain-driven design, a bounded context defines the boundaries of a specific model within which a ubiquitous language is consistent. Application. Each microservice or integrated system should ideally correspond to a bounded context, owning its data and logic. Integration then happens at the boundaries of these contexts, facilitating the use of canonical data models to translate between their unique languages. Why it matters: prevents model collision, promotes clarity, and simplifies data ownership. Eventual consistency. Definition: in distributed systems, data updates are not immediately consistent across all replicas or systems. Instead, they propagate over time, and all systems eventually reach a consistent state. Application: embrace event-driven architectures. Design services to react to events and update their local state. Use patterns like Saga, orchestrated or choreographed, to manage distributed transactions. Why it matters: essential for highly scalable and available distributed systems. Understanding and designing for eventual consistency is crucial for avoiding strong coupling and performance bottlenecks, but it requires careful handling of user experience, e.g., showing, processing, status, resilience, and fault tolerance. Definition: the ability of an integrated system to continue operating, perhaps in a degraded mode, despite failures of individual components. Application: assume failures will happen. Implement guaranteed delivery, idempotent consumers, dead letter channels, retry mechanisms, and circuit breakers. Design for graceful degradation. Why it matters: prevents cascading failures, minimizes downtime, ensures data integrity, and improves overall system reliability. Observability and monitoring integration flows. Designing a robust system is one thing. Understanding its behavior in production is another. In complex integrated environments, observability is paramount. Logging: ensure all key integration components, API gateway, message routers, transformers, service endpoints, produce rich, structured logs. Crucially, logs should include correlation IDs to allow tracing a single transaction across multiple systems. Metrics: collect key performance indicators, KPIs for each integration component, message throughput, latency, error rates, queue depths, processing times. Use dashboards to visualize these metrics. Tracing: implement distributed tracing, e.g., OpenTelemetry, Zipkin, Jaeger, to visualize the end-to-end flow of a request or message across all services involved. Correlation IDs are fundamental here. Alerting: set up alerts for anomalies detected in metrics or logs, e.g., high error rates, queue buildup, long latencies, unprocessable messages in dead letter channels. The control bus. As discussed in Chapter 7, a dedicated control bus can be used as a channel for publishing operational metrics and receiving configuration commands for your integration components. Without robust observability, your integrated system becomes a black box, and diagnosing problems or understanding performance bottlenecks becomes nearly impossible. Security considerations in integration. Integration systems, by their nature, facilitate data flow between multiple systems, making security a critical concern. Authentication and authorization. Secure interservice communication. Use mechanisms like OAuth2, JWTs, JSON web tokens, or API keys for service-to-service authentication. Ensure each service only has access to the resources and data it needs, principle of least privilege. API gateways are critical for authenticating external user systems and enforcing authorization policies before routing requests to internal services. Encryption. Encrypt data in transit, e.g., via TLS SSL for HTTP, HTTPS, or secure messaging protocols, and at rest, e.g., encrypting data in message queues or storage. Data protection. Implement tokenization, masking, or pseudonymization for sensitive personal or financial information where possible, reducing the surface area of attack. Input validation. Always validate inputs at the edges of your system and within each service that processes user data. Never trust data received from another system without verification. Threat modeling. Regularly perform threat modeling to identify potential vulnerabilities in your integration architecture. Evolutionary design. Adapting integration solutions over time. Integration is not a one-time project. It's an ongoing process. Business requirements evolve, new systems are introduced, and old systems are decommissioned. Your integration architecture must be designed for change. Version management. When designing APIs or evolving message schemas, implement robust versioning strategies, e.g., URL versioning like V1 users, header versioning for APIs, schema versioning for events. Backward compatibility. Strive to maintain backward compatibility for schemas and APIs. When breaking changes are unavoidable, provide clear migration paths and deprecation warnings. The strangler fig pattern concept. For replacing monolithic or critical legacy systems, don't attempt a big bang rewrite. Instead, gradually strangle the old system by routing new functionality or requests through a new, modern service, eventually replacing the old system piece by piece. This avoids high-risk migrations. Continuous refinement. Regularly review your integration landscape. Look for bottlenecks, anti-patterns, and opportunities for simplification or optimization. Integration debt accumulates quickly. Automation. Automate deployment, testing, and monitoring of your integration components to enable rapid, confident, and frequent changes. Conclusion: engineering seamless systems. Designing integrated systems is a complex endeavor that goes far beyond stringing together individual patterns. It requires a holistic understanding of integration styles, strategic build-or-buy decisions, and a steadfast adherence to core architectural principles like loose coupling, high cohesion, and resilience, coupled with strong observability practices, robust security, and an evolutionary mindset. These approaches transform chaotic system interactions into seamless, efficient, and adaptable flows. You are no longer just connecting applications. You are engineering the circulatory system of the modern digital enterprise, enabling it to thrive and evolve. In the next chapter, we'll reinforce this understanding by looking at common pitfalls and anti-patterns to avoid. Chapter 11: Pitfalls, Anti-Patterns, and Best Practices in Integration. We've covered a comprehensive set of enterprise integration patterns, explored how they apply to modern architectures, and discussed the strategic principles behind designing robust integrated systems. However, the path to seamless integration is fraught with common missteps. Knowing what not to do is often as important as knowing what to do. This chapter will highlight prevalent pitfalls and anti-patterns in integration, offering best practices to navigate these challenges and ensure your integration efforts lead to success rather than technical debt and frustration. Integration pitfalls, common traps to avoid. The integration spaghetti trap. Pitfall: connecting every system point to point without a consistent architectural approach. This creates a tangled mess where applications are tightly coupled, and tracing data flows or making changes becomes an impossible task. Why it happens: appears easy for small, initial integrations, lack of architectural foresight, desire for immediate results over long-term maintainability. How to avoid: embrace a central messaging paradigm. Use a message gateway, like an API gateway or a queue, as opposed to direct connections. Leverage patterns like content-based router or recipient list to manage fanout. Focus on loose coupling principles, Chapter 10. Overengineering and premature optimization. Pitfall: designing overly complex integration solutions for problems that could be solved simply, or prematurely optimizing for scale performance that isn't needed yet. This includes implementing patterns like CQRS or sagas when a simpler, even monolithic approach would suffice. Why it happens: chasing the latest and greatest architecture, fear of future technical debt, lack of clarity on current and immediate future requirements. How to avoid: start simple. Use the simplest pattern or strategy that solves the current problem effectively. Embrace evolutionary design, Chapter 10. Gradually introduce complexity, e.g., add an event bus after direct APIs become a bottleneck. Implement a saga only when distributed transactions truly require it. The YAGNI, you ain't gonna need it principle applies heavily. Ignoring data ownership and consistency. Pitfall: allowing multiple systems to directly own or modify the same data, leading to conflicts, data duplication, and an unclear source of truth. Why it happens: lack of clear domain boundaries, convenience over consistency, neglecting the importance of bounded contexts. How to avoid: establish clear data ownership. Each piece of data should ideally be owned by one service. Other services consume that data via events or APIs. Where data is shared or replicated, ensure a clear update mechanism, e.g., master-slave replication, or relying on eventual consistency with clear strategies like transactional outbox. Neglecting error handling and observability. Pitfall: building optimistic integration flows that assume everything will always work, or failing to implement proper logging, tracing, and monitoring. Why it happens: focus on happy path development, underestimating the complexity of distributed systems, lack of tooling or expertise. How to avoid: assume failures will happen. Implement guaranteed delivery, idempotent consumers, and use dead letter channels for unprocessable messages. Incorporate robust error handlers, Chapter 6. Implement correlation IDs for tracing. Invest in comprehensive logging, metrics, and distributed tracing. Use a control bus for monitoring. Lack of governance and standards. Pitfall: allowing each team to choose its own integration technologies, patterns, and protocols, leading to fragmentation and difficulty in enterprise-wide management. Why it happens: lack of architectural leadership, teams' desire for autonomy exceeding enterprise interoperability needs. How to avoid: establish clear guidance, architectural principles, and a recommended set of patterns and technologies. Promote shared services, e.g., a centralized message broker and API management platform. Encourage a canonical data model for critical entities. Provide clear documentation and training. Common anti-patterns in integration. Anti-patterns are recurring solutions to common problems that, despite appearing initially beneficial, ultimately lead to more harm than good. The smart pipes, dumb endpoints fallacy, aka fat ESB. Anti-pattern: centralizing all integration logic, routing, transformation, business rules, error handling within a monolithic enterprise service bus, ESB, while keeping the actual application endpoint simple. Why it's bad: the ESB becomes a bottleneck, a single point of failure, and a complex black box that's hard to change, test, and scale. It couples applications through shared logic within the ESB. Development becomes centralized around the ESB team. Correction: move intelligence and business logic to the endpoints, applications/microservices. The pipes, messaging channels brokers, should be dumb conveyors, simple and reliable. This aligns with microservices principles. Use the pipes and filters approach, where filters are distributed as services. Shared database as an integration mechanism. Anti-pattern: using a single database as the primary mechanism for multiple applications, services to exchange data. Why it's bad: direct coupling at the data schema level makes independent evolution impossible. Creates a central performance bottleneck and single point of failure. Correction: each service should own its data. Data exchange should happen via explicit APIs, messaging, events or commands, or transactional outbox for reliable propagation. Data duplication without source of truth. Anti-pattern: copying data across multiple systems without establishing a clear master source of truth for that data. Why it's bad: leads to data inconsistencies. Difficult to reconcile conflicting updates. Auditing becomes impossible. Correction: for every piece of enterprise data, identify a single system of record, SOAR. Other systems that require that data should consume it from the SOAR, e.g., via events using publish-subscribe channel, or through read-only APIs data replication. Use message enricher to get current data from SOAR when needed. Synchronous over-reliance. Anti-pattern: using synchronous RPC API calls for all inter-service communication, regardless of whether an immediate response is inherently needed. Why it's bad: creates tight coupling, propagates latency, and makes systems brittle in the face of temporary service unavailability. Correction: prefer asynchronous messaging for most internal service-to-service communication, particularly for long-running processes, events, and tasks where an immediate response is not strictly necessary. Reserve synchronous APIs for requests that genuinely require an instant response, e.g., user interface interactions. Polling instead of events. Anti-pattern: continuously querying a system, e.g., via cron jobs or timed API calls to check for changes, rather than receiving push-based notifications. Why it's bad. Inefficient, wastes resources checking for changes that haven't occurred, introduces latency, changes are only detected at polling interval, and places unnecessary load on the source system. Correction. Transform the source system to publish events when changes occur. If that's not possible, use a change data capture, CDC, mechanism or gateway that translates changes into events. Only use polling as a last resort, for legacy systems where no other option exists, or for very low-frequency checks. Best practices for seamless system design. Design for change, evolutionary architecture. Recognize that integration solutions are not static. Design with versioning, backward compatibility, and extensibility in mind. Prefer small, independent, composable components over monolithic integration platforms. Establish clear contracts and schemas. Define explicit APIs and message schemas for all integration points. Use clear, well-documented definitions, e.g., Open API Swagger for REST, Avro/JSON schema for Kafka messages. Agree on a canonical data model for core business entities where relevant between bounded contexts. Prioritize asynchronous communication. For most internal service-to-service interactions, especially events and long-running processes, design for asynchronicity using message queues and topics. This maximizes decoupling and scalability. Embrace idempotence. Design your message consumers to be idempotent consumers. Assume messages will be delivered at least once, and your logic should safely handle duplicates. Implement comprehensive observability. Ensure correlation IDs are passed through all messages and requests. Standardize logging, metrics, and distributed tracing. Set up proactive alerts for anomalies in your integration landscape. Automate everything possible. Strive for automated deployment pipelines, CI/CD, for integration components. Automate testing of integration flows, unit, integration, end-to-end tests, including negative scenarios and error paths. Automate monitoring and alerting. Right tool for the job. Don't force a complex pattern, like Saga or CQRS, onto a simple problem. Understand the trade-offs. Carefully weigh build versus buy for your integration solutions, considering your team's expertise and long-term costs. Security first. Treat integration points as potential attack vectors. Implement strong authentication, authorization, encryption, input validation, and adhere to the principle of least privilege. Conclusion. Continuous improvement and vigilance. Building seamless systems is a journey, not a destination. It requires constant vigilance, a willingness to adapt, and a deep understanding of not just the successful patterns, but also the common pitfalls and anti-patterns that can derail even the best-intentioned projects. By learning from the experiences of others, avoiding these common traps, and consistently applying the best practices outlined in this book, you can build integrated systems that are not only functional, but also resilient, scalable, maintainable, and truly enable your organization to thrive in a distributed world. The next and final chapter will cast an eye towards the future, exploring emerging trends that will continue to shape the world of enterprise integration. Chapter 12. The Future of Integration, AI, Serverless, and Emerging Trends. The world of enterprise integration is a constantly evolving landscape. Just as the emergence of the internet, service-oriented architectures, and microservices profoundly shaped how systems communicate, new technological waves are continuously reshaping our approaches to knitting applications together. While the foundational enterprise integration patterns we've explored throughout this book remain timeless conceptual tools, their physical manifestations, tooling, and the problems they solve continue to evolve. This chapter casts an eye toward the horizon, exploring some of the most impactful trends influencing the future of integration, from the rise of artificial intelligence to new paradigms in data architecture, AI and machine learning and integration, the intelligent orchestrator. Artificial intelligence, AI, and machine learning, ML, are moving beyond niche applications to infuse every layer of the technology stack, including integration. Their role in integration is not to replace the fundamental patterns, but to make them more dynamic, efficient, and intelligent. Intelligent routing and orchestration, beyond rule-based. Traditional routing, like the content-based router or recipient list, relies on predefined rules. AI can take this a step further, dynamically optimizing message routes based on real-time conditions, e.g., network latency, system load, geographical location, historical performance data, or even predicting congestion. Self-healing workflows. ML algorithms can analyze patterns of past failures and automatically adjust integration flows, retraying messages, redirecting to alternative services, or even preemptively scaling resources to prevent bottlenecks. Predictive maintenance. In IoT integration, discussed later, AI can analyze sensor data streams to predict equipment failures, triggering messages to maintenance systems before a breakdown occurs, rather than reacting to an alert after the fact. Anomaly detection and proactive monitoring. Integration flows, especially asynchronous ones, can be complex to monitor. AI can analyze vast streams of operational data, logs, metrics, message throughput, latency, to identify subtle anomalies that human operators might miss. This allows for proactive intervention before a small issue escalates into a major outage. Imagine an AI noticing a slight increase in message queue depth or a minor delay in a specific transformation step, and realizing it's a precursor to a system overload later in the day. Automated data mapping and transformation. The message translator pattern often requires significant effort to map disparate data formats. AI, particularly natural language processing, NLP, and machine learning from historical mappings, can assist in suggesting or even automatically generating complex data transformations. By analyzing data samples, AI could propose mappings between fields or suggest normalization rules, significantly accelerating integration development. Natural language integration. Imagine configuring or querying integration flows using natural language. AI-powered interfaces could allow developers or even business users to say, route all high-priority customer support requests to the VIP service, and the system automatically generates the necessary routing rules. While these applications of AI are promising, they are still evolving. Their successful implementation requires significant data, careful model training, and robust validation to ensure accuracy and prevent unintended consequences. Serverless integration, the event-driven frontier. We briefly touched upon serverless in Chapter 9, but its impact on integration is so profound that it warrants a deeper dive into its future. Serverless computing fundamentally redefines how we think about deploying and scaling integrated components. Functions as intelligent endpoints. Serverless functions, like AWS Lambda, Azure Functions, Google Cloud Functions, are the quintessential embodiment of intelligent message endpoints and filters. They are small, stateless pieces of code designed to execute in response to events. The orchestration layer. Cloud providers offer a rich suite of managed services for messaging, queues, topics, streams, data storage, and external connectivity. Serverless functions often act as the glue or transformation layer between these managed services. An incoming message from a queue can trigger a function that transforms the data, which then triggers another function to store it or sends a new message to a different topic. This creates implicit pipes and filters pipelines. Built-in EIPs. Serverless environments inherently provide many EIP functionalities out of the box, though often as managed services, guaranteed delivery, handled by the underlying managed messaging service. Competing consumers, built into how functions scale with queue loads. Error handling retries, configurable retry policies for functions integrated with various event sources. API gateway integration, seamlessly connect HTTP requests to functions. Benefits unlocked, auto-scaling. Functions automatically scale from 0 to massive concurrency based on demand, eliminating manual scaling effort. Cost efficiency, you only pay for the actual computation time, not for idle servers. Reduced operational overhead. Cloud providers manage the underlying infrastructure, patching, and security. Challenges and future. While powerful, serverless still faces challenges like cold starts, initial latency for a function to spin up, debugging stateless functions across distributed traces, and potential vendor lock-in to specific cloud ecosystem integrations. The future will see more sophisticated debugging tools, faster cold start times, and potentially portable serverless runtimes. Integration Platform as a Service, EIPs, and low-code, no-code integration. The demand for faster integration and lower development barriers is driving the growth of EIPs and low-code, no-code platforms. EIPs evolution. Moving beyond the monolithic ESB, modern EIPs solutions, e.g., MuleSoft Anypoint, Dell Boomi, Workato, Azure Integration Services, AWS Step Functions Event Bridge, provide cloud-native distributed platforms for integration. They offer pre-built connectors to popular applications, visual designers for orchestrating workflows, and managed runtime environments for integration flows. They essentially wrap and manage many EIPs as configurable services. Low-code, no-code empowerment. These platforms democratize integration by allowing business analysts or citizen integrators to build simple to moderate integrations using drag-and-drop interfaces and predefined components without writing traditional code. Impact on EIPs. Abstraction. They abstract away the implementation details of EIPs, presenting them as configurable components, e.g., a connector, which is a specialized message endpoint, a flow designer, which is a visual pipes and filters builder, or a router component that hides the complexity of a content-based router. Accelerated delivery significantly reduces the time and specialized skill required to connect applications. Hybrid integration. Many EIPs platforms excel at connecting cloud-native applications with on-premises legacy systems. Future trends. Expect continued growth in this area, with more sophisticated AI-driven mapping, more robust error handling out of the box, and deeper integration with broader enterprise automation and workflow platforms. The line between business process automation, workflow engines, and integration platforms will continue to blur. Data mesh and distributed data architectures. While our focus has largely been on application integration, the future of data management is also heavily influencing integration strategies. The data mesh paradigm, conceptualized by Zhamak Dehghani, proposes a shift from centralized data ownership, e.g., a central data lake team, to decentralized, domain-oriented teams owning and serving their data as data products. Core idea: data is treated as a product, owned by the domain that produces it, and exposed as discoverable, addressable, trustworthy, and secure datasets. Impact on integration. Shift from ETL to ELT events. Instead of central ETL pipelines pulling data from various sources, data domains publish their data as events or streams, often using publish-subscribe channels like Kafka. Other domains interested in this raw data consume it and perform their own local transformations, message translators, to fit their needs. Data products as APIs. Each domain is responsible for exposing its data as a data product, often through well-defined APIs. This ensures high-quality, curated access points. Decentralized event streaming. Emphasis on robust, distributed event streaming platforms like Apache Kafka as the fabric for interdomain data exchange. EIPs are fundamental. Data mesh relies heavily on the event message, publish-subscribe channel, message translator, canonical data model within domains, and message endpoint patterns, but applied at a much larger, more decentralized scale across the enterprise. It also implicitly reinforces the control bus concept for global data governance and discovery. Future direction. This model prioritizes decentralized ownership and self-service, promoting highly localized integration points based on standardized contracts, shifting the burden of transformation onto consumers where appropriate. Beyond traditional EIPs, stream processing and IoT integration. Finally, two areas are pushing the boundaries of what integration means, demanding new applications and specialized implementations of EIPs. Stream processing. Concept. Moving beyond processing discrete messages, stream processing platforms, e.g., Apache Kafka Streams, Apache Flink, Spark Streaming, enable continuous, real-time computation on unbounded streams of data. It's not just about moving data. It's about continuously transforming, enriching, aggregating, and analyzing data as it flows. EIP relevance. All core EIPs filter, transform, enrich, splitter, aggregator are implemented as real-time stream operations. For example, a message enricher might join an incoming sensor reading stream with a static reference data stream in real time. A resequencer can reorder events in a stream. Future. Expect deeper integration of stream processing with AI ML for real-time analytics, anomaly detection, and predictive actions directly on streaming data. Internet of Things, IoT, integration. Concept. Integrating vast numbers of physical devices, sensors, smart appliances, industrial machinery that produce continuous streams of telemetry data or require remote commands. EIP relevance, high-volume messaging, requires specialized, lightweight messaging protocols like MQTT to handle millions of devices. Scalable channels, demand extremely scalable message channels capable of ingesting massive data volumes, often backed by event streams. Message filtering and transformation, essential at the edge, close to devices, and in the cloud to filter out noise, normalize data from heterogeneous devices, and enrich sensor readings with context, e.g., location, device ID. Command messaging, sending commands from the cloud to devices, e.g., turn off light, adjust temperature, is another form of command message over a point-to-point channel to a specific device endpoint. Edge computing. Integrations are increasingly happening at the edge. Data is processed, filtered, and occasionally aggregated closer to the IoT devices before being sent to the cloud, reducing latency and bandwidth. This means EIPs are being implemented in distributed, often resource-constrained edge environments. Conclusion: the enduring power of patterns in a dynamic world. The future of enterprise integration is dynamic and exciting, driven by the relentless march of technological innovation. AI will make our integration smarter, serverless will make it more agile and cost-effective, EIPs will democratize its creation, and new architectural paradigms like data mesh will redefine how data moves across the enterprise. IoT and stream processing will continue to push the boundaries of real-time data handling. In this ever-changing landscape, one truth remains constant. The enterprise integration patterns are the durable, fundamental principles that will continue to guide architects and developers. They provide the universal language needed to describe and solve complex integration challenges, ensuring that even as the specific technologies and tools evolve, our ability to connect disparate systems into seamless, intelligent, and resilient ecosystems will only grow stronger. The journey to seamless systems is an ongoing one, fueled by continuous learning and the timeless wisdom embedded in these patterns. Chapter 13, Journey to Seamless Systems, Asynthesis and Next Steps. We have reached the culmination of our journey, from the foundational concept of a message to the intricate coordination of sagas, and from the legacy of ad hoc connections to the promise of AI-enhanced integration. We've systematically explored the landscape of enterprise integration patterns. The path to building seamless systems is not always straightforward, but the principles and patterns we've discussed provide a powerful compass. The core message throughout this book has been clear. In a world of ever-increasing distribution and specialization, integration is not an afterthought, but a core architectural discipline. It is the art and science of ensuring that independent components, often built by different teams, using different technologies, can nevertheless communicate, cooperate, and evolve to drive holistic business value. The timeless toolkit for a modern world. Let's briefly recap the essential concepts and patterns that form your integration toolkit. The fundamentals, messages, channels, endpoints. These are the atomic elements, the ABCs of how systems talk. Understanding the distinction between point-to-point and publish-subscribe channels is paramount for managing coupling. The flow orchestrators, routers, splitters, aggregators. Patterns like the content-based router, recipient list, splitter, and aggregator allow you to direct, segment, and reassemble messages with surgical precision, enabling complex workflows and parallel processing. And the resequencer ensures order when it matters most. The interpreters, translators, enrichers, normalizers. Bridging semantic and structural gaps is vital. The message translator, message enricher, and normalizer, often guided by a canonical data model, ensure that data is always understood, no matter its origin or destination. The guardians of reliability, guaranteed delivery, idempotence, error handling, failures are inevitable. Your systems must be resilient. Concepts like guaranteed delivery, the idempotent consumer, dead letter channels, robust error handlers, and the competing consumers pattern are crucial for fault tolerance and scalability. The transactional outbox pattern ensures atomic data publication. The coordinators of complexity, commands, events, sagas, moving beyond simple data transfer, the distinction between commands and events enables powerful microservices architectures and event-driven architectures. The saga pattern provides a robust mechanism for coordinating long-running distributed transactions. The enablers of visibility, correlation ID, control bus, you cannot manage what you cannot see. The correlation identifier is your indispensable tool for tracing end-to-end transactions, and the control bus and modern observability platforms provides the means to monitor and manage your integrated ecosystem. Crucially, we've seen how these enduring patterns are not relics of a past era, but the very principles underpinning contemporary architectural styles. The API gateway embodies the message gateway. Service meshes implement message routers and circuit breakers. Event-driven architectures are fundamentally built on publish-subscribe channels and event messages. Serverless functions often serve as intelligent message endpoints and filters. The timelessness of these patterns assures their continued relevance in any new technology or paradigm that emerges. The integration developer's mindset. More than just knowing the patterns, successful integration developers cultivate a specific mindset. Embrace loose coupling. This is the golden rule. Prioritize designs that allow systems to evolve and fail independently. Question any decision that would tightly bind components. Design for failure. Assume networks will fail, services will crash, and messages will get lost or duplicated. Your design must account for these realities, not ignore them. Think asynchronously. While synchronous interactions have their place, train yourself to see opportunities for asynchronous, event-driven communication. It pays dividends in scalability and resilience. Understand the business domain. Integration isn't just about technology, it's about enabling business processes. A deep understanding of the why behind the data flow will lead to more effective and meaningful integrations. Prioritize observability. Make your distributed systems transparent. Ensure you can pinpoint where problems occur and understand the end-to-end flow of every transaction using logs, metrics, and tracing. Seek simplicity. While integration is complex, strive for the simplest solution that solves the problem. Avoid over-engineering and premature optimization. Be data-centric. Understand data ownership, its life cycle, and how its consistency is maintained across bounded contexts, whether through eventual consistency or more rigorous means. Be a pragmatist. There is no one-size-fits-all solution. Be prepared to choose the right tool for the job, even if it means a hybrid approach, blending different integration styles and technologies. Beyond the book, continuous learning. The field of software development and integration within it is in a state of perpetual motion. New tools, frameworks, and architectural paradigms are constantly emerging. Your journey to seamless systems doesn't end with this book. It's an ongoing commitment to learning and adaptation. Dive deeper into the original source. If you wish to explore the patterns in even greater depth, revisit Enterprise Integration Patterns, Designing, Building, and Deploying Messaging Solutions by Gregor Hope and Bobby Wolf. It remains the foundational text. Explore specific technologies. If an EIP concept resonates, research how it's implemented in actual technologies like Apache Kafka, RabbitMQ, Apache Camel, Spring Integration, Azure Integration Services, AWS Step Functions, or relevant EIPs platforms. Read about emerging trends. Keep an eye on new developments in areas like data mesh, stream processing, distributed ledgers, AI/ML in operations, and new communication protocols. Practice, practice, practice. The best way to internalize these patterns is to apply them. Start small, experiment, build prototypes, and analyze how real-world challenges manifest as instances of these patterns. Your journey to seamless systems. You are now equipped with a powerful conceptual framework and a common language to tackle the multifaceted challenges of enterprise integration. Building seamless systems requires patience, attention to detail, a willingness to collaborate across teams, and a deep understanding of how software components should interact. Remember, every time you design two systems to communicate, you are performing an act of integration. By applying these patterns, you are not just connecting applications. You are engineering the nervous system of modern digital enterprises, enabling them to be agile, resilient, and responsive. Go forth and build seamless systems. The connected world depends on it.